The ocean planet model was initially proposed by the New Zealand astronomer David J. Stevenson of the California Institute of Technology, Caltech, at the turn of the 21st century. This model was then further developed by the team of Christophe Sautin, planetologist and professor at Nantes University. At the origin of the discovery of ocean planets, there is the phenomenon of planetary migration. We speak of planetary migration when a planet moves closer to its star after its formation. This theory was developed to explain the discovery of gas giants too close to their star to have formed there. The first ocean planet was discovered by calculation on December 16, 2009. It was named GJ1214b, or Gliese 1214b, and is located in the constellation of Serpentarius at about 40 light-years from the Sun. We will explore this ocean planet a little later in this trip. But then, how did astronomers come to the conclusion that the ocean planets of science fiction could really exist? Since the middle of the 20th century, even before the discovery of the first exoplanet, important discoveries have been made concerning the presence of water in the universe. In particular, scientists looked at the moons of Jupiter and Saturn. In the 1970s, NASA scientists became interested in Ganymede, a moon of Jupiter, where they suspected the presence of a thick underground ocean sandwiched between two layers of ice. Lewis's work showed in 1971 that radioactive decay could, especially in the presence of ammonia, produce underground oceans in large moons. The search for water on Mars has also been the subject of numerous studies and space missions. Since the first exoplanet was discovered, astronomers are now looking for evidence of liquid water beyond our own solar system. In 2004, Alain Leger, a researcher at the Institute of Space Astrophysics, calculated with his team that a small number of icy planets formed on the outskirts of their star could migrate inwards by up to 1 astronomical unit, the distance between the Earth and the Sun. This migration would melt the ice of the outer layers, forming ocean planets. Today, the existence of ocean planets is no longer a simple scientific hypothesis. Observations from the Hubble telescope, as well as information gathered by space probes such as Galileo, Pioneer, Voyager, or Cassini-Huygens, indicate that several bodies in the universe could harbor liquid water under an insulating shell of ice. But not only. Because the model of the typical ocean planet can vary depending on multiple factors, including the composition of the atmosphere. In June 2020, NASA scientists asserted, based on numerical models, that it is likely that ocean exoplanets are common in the Milky Way galaxy. The first potentially habitable ocean exoplanet was discovered just recently, in June 2022, by the Transiting Exoplanet Survey Satellite. It was named TOI 1452b. Like Gliese 1214b, we will explore it later in this trip. In the meantime, we will discover why ocean planets interest scientists so much. We now know that ocean worlds most certainly exist, even though there is no direct evidence for their existence. Why has this discovery been so important to the scientific community? What is it about these entirely water-covered planets that interests astronomers so much? According to Li Zhang, a researcher at Harvard University, and his team, who classified the exoplanets according to their radius, 1/3 of the known exoplanets are ocean planets. They would thus be billions in the galaxy, and more than 1/3 of the exoplanets discovered would be covered with half water. The Earth is not the only blue planet in the universe. This is good news for astrophysicists who are looking for extraterrestrial life. Astronomers Raphael Luque, a postdoctoral researcher at the University of Chicago, and Enric Palé of the Institute of Astrophysics of the Canary Islands and the University of La Laguna have published an interesting paper in the journal Science. Their study focused on the occurrence of ocean planets around M-type red dwarfs, the most frequent stars in the universe. The conclusion of the study showed that ocean planets are surprisingly frequent around stars of this type. The search for oceanic worlds is important for the search for extraterrestrial life, because water is the origin of life, at least on our planet. This is why NASA is taking a close interest in Europa and Enceladus, icy moons of Jupiter and Saturn. Geysers have been observed on the surface of these moons. The objective of the next exploration missions will be to find molecules of biological origin in the particles spewed by these geysers. It is already known that these two moons have an ocean under an ice pack, and that they are subject to strong tidal forces that cause volcanic activity. This volcanic activity could imply the existence of hydrothermal hotspots at the bottom of these icy oceans. On Earth, these hot springs are home to many forms of life. In the absence of sunlight, it is chemosynthesis that allows living organisms to develop there. Let's look at this in more detail so that you can better understand why, like the icy moons Europa and Enceladus, the ocean planets are of interest to scientists. Water and energy are two essential criteria for the development of life as we know it. Ocean planets already contain water, so it is not surprising that they interest astrophysicists in search of an extraterrestrial life form. Especially if these ocean planets are located in the habitable zone of their star, i.e., neither too close nor too far away, so that the temperature, gravity, and pressure conditions are optimal. If it is proven that an ocean planet does contain water in a liquid state, all that remains is to determine a source of energy. The energy released by the planets in the form of heat can come from two sources: the tidal force or the decay of radioactive materials that compose their mantle and crust. The tidal force depends on the elongation of the orbit of the exoplanet. The decay of radioactive materials depends on the mass of its mantle and the age of the planet. Hence the importance, in order to refine the models, of being able to determine with precision the characteristics of the potential oceanic exoplanets observed. And then, is water and energy sufficient for the emergence of life? Planets can evacuate the heat produced by the tidal force or by the decay of radioactive materials via volcanism and tectonics. For a planet to be habitable, It must therefore have volcanic or tectonic activity, but not too much either. Let's get back to Li Zhang and his team. This researcher from Harvard University has used analyses from the European Space Agency's Gaia satellite to develop a new system for classifying exoplanets based on the constant RT for Earth radius. This new model makes it possible to explain the relationship between the mass, the radius, and the composition of exoplanets. A real step forward to better understand their formation and predict ever more accurate models. This new model shows in particular that the formation and the internal structure of planets are constrained by their dimensions. According to the system developed by Li Zhang and his team, planets with a radius of less than 2 RT are rocky and poor in water. Planets with radius between 2 and 4 RT are water-rich ocean planets. Between 4 and 10 RT, they are planets rich in gas. Beyond a radius of 10 RT, they are gas giants, composed mainly of hydrogen and helium. Li Zhang and his team have put forward an interesting hypothesis to explain the formation of ocean planets. These planets would have formed like gas giants, but would have eventually evolved differently to become water-rich planets. They are at the limit between a super-Earth and a gas giant, with a mass 8 to 10 times greater than that of the Earth. Ocean planets are numerous, but they are not all habitable. This is where the challenge lies in order not to get lost in endless research. We must know how to distinguish between those that are potentially habitable and those that are not. Ocean planets are interesting for scientists looking for extraterrestrial life, but not only. Even if they are not habitable and do not harbor life, they remain objects to be studied because they provide clues about the formation and evolution of planets, and thus of our solar system. Fasten your seatbelt. We are now going on a journey to the very heart of the ocean planets. What can you expect on this journey? Are the ocean planets similar to Earth? According to studies and models, ocean worlds would not be quite like the Earth, or even like Camino in Star Wars, but rather like the moons of Jupiter and Saturn, Ganymede, Europa, and Enceladus. Let's briefly recall the methods used by scientists to detect exoplanets, and therefore ocean planets. Exoplanets can be detected via the transit method, or via the radial velocity method. The transit method consists in detecting variations in the luminosity of a star when the planet orbiting it passes between the star and the observer. This is called a transit. The transit method allows us to deduce the radius of the exoplanet. The radial velocity method is the one used by the James Webb Telescope. This one embeds a spectrograph, which can highlight a Doppler effect. The Doppler effect is the apparent change in the frequency of a sound or electromagnetic signal from a moving object received by a fixed observer. This method measures the oscillation of a star in response to the gravitation of an exoplanet as the star moves towards or away from us. It works whether there is a transit or not. But if there is a transit, it is always better. This method would then allow us to determine the mass of the exoplanet, its radius, and therefore its density, which allows us to deduce its composition. Valuable information to detect ocean planets. These methods allow us not only to detect exoplanets, but also to know if they are gas giants or rocky planets. The observation of potential ocean planets with these methods has shown us that there would be a typical structure for ocean planets, which would be similar to that of the Jovian satellite Ganymede. Ocean planets would be composed of a core of iron, a mantle of ice and rocks, and a surface ocean, salty or not. How is an ocean planet formed according to scientists' models? Let's go back to the beginning of our solar system to better understand the mechanisms of formation of these aquatic worlds. The formation and evolution of the solar system is described by the model of the solar nebula hypothesis, developed in the 18th century by Immanuel Kant and refined over the centuries. Our solar system would be born from the gravitational collapse of a small part of a nebula. Nebulae are giant molecular clouds. The largest part of the cloud would have formed the Sun, and the scattered remains around the Sun would have formed the protoplanetary disk. This disk, composed of gas and dust, then served as a basis for the formation of planets, moons, and asteroids. In each planetary system, there is what is called the ice line. You may also hear it referred to as the ice line, frost line, or snow line. Whatever you call it, this fictitious line is the boundary between which a given chemical species exists in solid form. In other words, before the line, the species is in the form of gas, and after the line in the form of ice. There is therefore one frost line per chemical species, although this term is generally used to refer to the ice line of water. In the outer solar system, i.e., beyond the planet Mars, planetary objects are born from a structure similar to a comet, i.e., a mixture of water and rocks. They are then less dense than rocky planets. Their composition depends on their position relative to the frost line. Planets and icy moons that form near the frost line contain mainly water and silicates. And planets that form further away may contain, in addition to ammonia, methane, carbon monoxide, nitrogen, and carbon dioxide CO2. As the protoplanetary disk dissipates, the planets that formed further inside the disk will tend to migrate closer to the Sun. Planets that formed in the outer regions and migrated inward are more likely to contain abundant water than planets that formed near the star. A water-rich planet near its star was therefore formed farther away from the star before moving closer to it. The migration of icy planets to the interior of the star system involves the ice melting and becoming liquid, which transforms icy planets into oceanic planets. When a planet forms, much of the water in the planet is initially trapped in the mantle. As the planet cools, the mantle begins to solidify, and large amounts of water, between 60% and 99% of the total amount in the mantle, dissolves to form a vapor atmosphere. This atmosphere can condense to form an ocean. A heat source is therefore necessary to form an ocean. It can be, as you have seen, scientists are trying to establish models of the structure of an ocean planet once it is formed. The structure of an ocean planet depends on many factors and can be inferred from its density, shape, and gravitational pull. Studying an exoplanet can allow scientists to determine whether or not the celestial body has undergone differentiation, that is, separation into rock and ice layers. The small icy moons are made of a layer of water on a silicate core. In the case of Enceladus, the ocean is located between a solid shell of ice on the surface and the silicate core. Since the ocean is in direct contact with the silicates can provide hydrothermal and chemical energy to low-complexity life forms. But Ganymede, which is larger and contains more ice, has an even different and more complex structure. The pressures are high enough that there is an ocean between two ice shells. Imagine a sandwich with the ice instead of bread and the ocean as a filling. The filling of a sandwich is always composed of several elements or layers. This is also the case for Ganymede and the large ocean planets. As the pressure is variable at depth, water worlds may well have a structure that alternates phases of steam, liquid water, high-pressure ice, and plasma. Some of the water contained in ocean planets could take the form of Ice 7, a crystalline form of ice that is stable at high pressure. Let's stop for a minute to think about Ice 7, because it is a fascinating concept. This ice form was modeled by American physicist and Nobel Prize winner Percy Williams Bridgman in 1937. In 2017, it was observed directly in the form of inclusions present in diamonds mined at the Oropa mine in Botswana. These diamonds were formed in the transition zone of the Earth's mantle between 410 and 660 kilometers, or 250 and 410 miles deep, as liquid water subjected to very high pressures and temperatures. When the diamonds were brought up, the liquid water crystallized because of the drop in temperature, the pressure remaining about the same due to the rigidity of the diamond. The ocean of water worlds, thus trapped between two layers of ice, could be maintained if the ratio between the speed of internal heating and the speed of evacuation of the heat is favorable. The heating by the tidal force is thus a criterion of choice in the study of the oceans of these aquatic worlds. The one does not go without the other. Astrophysicists who study ocean worlds must also take into account these characteristics to better understand their structure, since they cannot go there to make direct observations. Smaller ocean planets of less than 1 Earth mass would have, according to the models, a less dense atmosphere and a weaker gravity. Liquid water could thus evaporate more quickly. But liquid oceans could be fed by hydrothermal activity, or tides, for example. Once again, a fragile balance that all potentially aquatic planets may not be able to maintain over time. Let's now move closer to an ocean planet to see what its composition could be. If we take the example of our Earth, water covers 70.8% of the planet's surface, but represents only 0.05% of its mass. The Earth is therefore not what we call an oceanic world. This percentage is much higher in the case of an ocean planet. For example, in the case of TOI 1452b, the first potentially habitable ocean exoplanet discovered in 2022, liquid water would represent 30% of the planet's mass. Does it surprise you that the oceans of oceanic worlds represent such a high fraction of their mass? Actually, it's not that surprising. Models suggest that watery planets have oceans so deep and dense that even at high temperatures, the pressure would turn the water into ice, allowing a mantle of complex ice forms like V-ice to form. V-ice is not necessarily as cold as the ice you know on Earth. Yet another fascinating form of ice. For liquid water on the surface of an ocean planet to remain liquid for long periods of time, the planet must orbit in the habitable zone of its star, also called the Goldilocks zone. Its gravitational attraction must be able to maintain sufficient atmospheric pressure to retain the water so that it does not evaporate into space beyond its atmosphere. According to the models, a powerful planetary magnetosphere is needed to protect the atmosphere from mass loss due to stellar winds and to retain the water. Either the atmosphere of a planet is formed by outgassing during the formation of the planet, or it is captured gravitationally from the protoplanetary nebula. It is the greenhouse gases of the atmosphere that will govern the surface temperature of an exoplanet. Greenhouse gases will also absorb and redistribute energy from the star around which the ocean planet orbits, which can give valuable clues about the composition of the atmosphere. The composition of a watery exoplanet and its atmosphere depends, among other things, on its position relative to its star. If the planet is close enough to its star for the liquid water to reach its boiling point, the water would reach a supercritical state. We speak of a supercritical state when water is subjected to high temperatures and pressures, but not to the point of becoming solid. If the ocean planet is colder, then the atmosphere could be much thicker than that of the Earth, and composed largely of water vapor, which could produce a greenhouse effect. The planet would then have to be small enough or close enough to its star for the hydrogen and helium to be volatile. Otherwise, it would be the equivalent of an ice giant, like Uranus and Neptune, but hotter. Icy planets that have migrated to the interior closer to their star could develop thick vaporous atmospheres and thus retain their volatiles for billions of years, even in the event of atmospheric leakage. Atmospheric leakage is caused by ultraviolet radiation and leads to the erosion of the atmosphere, as well as the eventual loss of the oceans. Indeed, atmospheric leakage also means leakage of water vapor, and therefore leakage of hydrogen and oxygen into space. Models estimate that the amount of water lost is roughly proportional to the mass of the planet. You have understood that there is not only one model of atmosphere for the ocean planets. On the contrary, there are many possibilities. However, because a general model must be developed, scientists have estimated that the composition of the atmosphere of an icy planet that became an ocean planet would be about 90% water, 3% ammonia, and 5% carbon dioxide. Now that you have understood how ocean planets are formed and what these watery worlds look like, you are probably wondering if life can develop on them. Can life forms be found on these ocean planets? Or even better, an intelligent extraterrestrial civilization? Are ocean planets inhabited, like the Camino planet from Star Wars? The first thing to know is that if the planet is entirely covered with water on the surface, then the development of terrestrial life seems unlikely. And if there is a layer of solid, pressurized ice between the liquid water and the rocky mantle, the development of life as we know it is even less likely. Scientists have addressed this issue by studying hypothetical ocean worlds. In the case of an ocean planet covered with 5 terrestrial oceans of water, it would not contain enough phosphorus for terrestrial ocean organisms such as plankton to develop. Plankton is an oxygen producer and therefore plays a crucial role in the oceanic ecosystem on Earth. On Earth, phosphorus, which is essential for its development, reaches the oceans through rainwater that has hit the rocks of the land. A mechanism that could not work on a planet entirely covered by oceans. Another simulation investigated the hypothesis of an ocean world containing 50 terrestrial oceans of water. The pressure on the ocean floor would be so great that there would be no plate tectonics. Without plate tectonics, there is no volcanism. And without volcanism, there is no chemical environment for the development of life as we know it on Earth. However, these observations do not mean that there can be no life on ocean planets. Small ocean worlds like Europa and Enceladus are considered habitable environments because the oceans are in direct contact with the silicate core. Now, the silicate core is a potential source of heat and can also provide chemical elements that could be the origin of life. In addition, according to some researchers, the thick underground ice sheet could be a means of transport for some ingredients of biotic activity. According to a study published in the scientific journal Nature Communications in June 2022, there could be exchanges between the core and the ocean, despite the presence of a thick ice sheet. Until now, scientists thought that this ice, type 7, was too dense and prevented any contact between the ocean and the core. But finally, this ice is not so impermeable as we thought, and it could bring some chemical elements to the surface. In addition, in 2021, a bioscience study led by Jeffrey Dick and Everett Schock of Arizona State University showed that organisms can thrive on the seafloor without light. This would also be possible on other planets, and thus in ocean worlds. On Earth, life is possible through a mechanism called cellular respiration, which involves the intake of oxygen and the release of carbon dioxide. But this mechanism does not work in the ocean depths without heat or light. This does not mean that there is no life on the seafloor. The study has shown that at the bottom of the oceans there are some specific hydrothermal environments that can harbor complex organisms. This is the case, for example, of hydrothermal vents or hydrothermal mounts, vents located on the axis of oceanic ridges that were formed as a result of tectonic plate movements. Around these vents, hot fluids mix with very cold seawater, an environment that may seem extreme, but is nevertheless conducive to the development and life of tiny organisms. When the vents are composed of ultramafic rocks, magmatic rocks that are very low in silica and produce a lot of hydrogen, this is particularly favorable for the biosynthesis of the basic elements of cells, like amino acids and sugars. Even more energy is needed for a reaction called polymerization, which will create larger molecules such as proteins. This study shows that even in a particularly inhospitable ocean environment, life can be born and develop. This gives hope to scientists who believe that ocean planets could harbor an extraterrestrial life form. If it exists, life on an ocean planet would be very different from life in our terrestrial oceans. For one thing, the oceans themselves would not look anything like our own. The oceans of these aquatic planets would probably be subject to violent storms. Cyclones would form and suck water vapor over the oceans, and since they could not lose their strength over land, they would cause huge waves of several tens of meters high. If there was life in the oceans of the water worlds, then it would have developed rather in the depths, in a calmer zone, or else life would not be easy. Now that you have understood what an ocean planet is, and that you have had a glimpse of what such a planet would look like, we are going to take a trip to the heart of the most famous ocean planets. On this trip, we will go as far as 219 light-years away. You will be able to observe Gliese 1214b, the first ocean planet ever discovered, and TOI 1452b, a potentially habitable ocean planet, discovered in 2022. You'll also see K218b, the first exoplanet in the habitable zone where traces of water have been found. And we'll explore multi-planetary systems like TRAPPIST-1, Kepler 62, and Kepler 138, which host several planets, including ocean worlds. Fasten your seatbelt and take off for the watery worlds of our universe. Let's start with Gliese 1214b. This is the first ocean planet that was discovered by calculation on December 16, 2009. This super-Earth, located at 40 light-years from us, is in orbit around the star, Gliese 1214, in the constellation of Serpentarius. Its mass is 5.5 to 7.5 times that of the Earth, and its radius is 2.6 times that of our planet. Its average density is low, 2 grams per cubic centimeter. To give you an idea, the density of the Earth is 5.5 grams per cubic centimeter. This ocean planet would be, according to the estimates, composed to 75% of ice and to 25% of rock and metal. According to this hypothesis, the ocean of ice would be 13,000 kilometers, or 8,000 miles deep, and the rocky core would have a radius of 4,000 kilometers, or 2,500 miles. Close to its star, GJ 1214b would have a surface temperature of about 200 degrees Celsius, or 392 degrees Fahrenheit. Its atmosphere is 200 kilometers, or 125 miles thick, and would favor a greenhouse effect. The presence of life as we know it remains unlikely. Observations of this planet have been made by the Hubble telescope's Wide Field Camera 3, the most advanced instrument on board the telescope to take images in the visible spectrum. According to these observations, Gliese 1214b would be a largely gaseous planet with a high amount of water in its atmosphere. The atmosphere of the planet would be composed of 50 to 85% of water molecules. But how was the presence of water in the atmosphere of Gliese 1214b revealed? In a 2018 study published in the Astrophysical Journal, Japanese scientists demonstrated that the planet's atmosphere did contain water using 2 optical cameras on the Subaru telescope on the island of Hawaii. the scientists waited for the planet to pass in front of its star to analyze the light passing through its atmosphere. For this analysis, they used the phenomenon of Rayleigh scattering, a light-scattering phenomenon that occurs when light particles are scattered without a change in wavelength. Installing a blue filter on the cameras of the Subaru telescope made it possible to determine the intensity of the Rayleigh scattering phenomenon. Since the scattering was weak, the scientists concluded that the atmosphere of Gliese 1214b is rich in water. But this conclusion must be refined because a weak Rayleigh scattering can also mean that the atmosphere is dominated by hydrogen and very cloudy. The observations also confirm that this ocean planet was initially formed far from its star, that it was rich in ice, and that it would then have migrated to approach Gliese 1214. Some of the water on this planet could be in the form of hot ice in an exotic state. The exotic state is one of the four possible states of matter, with a gaseous state, the liquid state, and the solid state. Or, water would form a supercritical ocean due to the temperature and pressure conditions. Supercritical water is obtained on Earth by heating water to temperatures above 374 degrees Celsius, or 705 degrees Fahrenheit, under a pressure of more than 221 bar. It is a powerful solvent for all organic compounds. If the oceans of Gliese 1214b were in a supercritical state, life would most likely not be able to develop there. Let's continue our exploration of the exoplanets most likely to be oceanic worlds. Located 100 light-years from Earth in the Dragon constellation, TOI 1452b is the most talked about oceanic exoplanet at the moment because it was discovered just recently, in June 2022. This exoplanet orbits a red dwarf star located in a binary system, which is smaller than the Sun. The two stars of this binary system are separated by 97 astronomical units, which is about 2.5 times the distance between the Sun and Pluto. TOI 1452b can be called a super-Earth because its mass would be equivalent to 4 to 5 times that of the Earth, and it would be 70% larger. TOI 1452b was discovered by an international team led by astronomers from the Université de Montréal. To discover this ocean planet so far from our planet, they used data from NASA's TESS Space Telescope. The main function of the TESS telescope is to observe the celestial vault in search of planetary systems close to our own. To do this, the telescope watches for minute decreases in brightness that are caused by the passage of a planet in front of its star. This passage is called a transit. The analyses of TOI 1452b estimate that 30% of its total mass would be water. The water could be in liquid form on the surface, since the planet orbits in the habitable zone of its star. Observations from the TESS telescope have also shown that TOI 1452b orbits its star in 11 days. To determine the mass of TOI 1452b, scientists observed the binary star system with a Spirou instrument that has been installed on the Canada-France-Hawaii telescope since 2018. The Spirou instrument consists of a high-precision spectropolarimeter and velocimeter and operates in the near-infrared. The objective of this instrument is to locate exoplanets located in the habitable zone of their star, but also to observe the magnetic fields of protostars, i.e., stars that are only a few 100,000 years old. The goal is to finally unravel the mystery of how stars are born. Spiru measures the minute variations in the speed of stars that are caused by the planets orbiting them. With this instrument, researchers were able to estimate the mass of TOI 1452b at about 5 times that of the Earth. According to all the observations that have been made since the discovery of this exoplanet, TOI 1452b is probably a rocky planet, but with a density much lower than what we expect from a rocky planet like Earth. Observations that make scientists lean in favor of an ocean planet. According to them, TOI 1452b would even be one of the best candidates for the title of ocean planet discovered to date. Separated from the Sun by a relatively short distance on the scale of the universe, 100 light-years, TOI 1452b does not cease to interest astronomers. The James Webb Telescope, launched in December 2021, should help them to establish an even more precise portrait of this ocean planet. Let's continue our journey to the heart of the ocean planets of our universe. Located 40.5 light-years away in the constellation Aquarius, the TRAPPIST-1 system has fascinated astronomers since the discovery of 7 exoplanets around the red dwarf star, TRAPPIST-1a. Not only because 3 of these 7 planets are located in the habitable zone of the star, and are therefore likely to harbor life, but also because such a number of planets in the same system could tell us a lot about the formation of our own solar system. Compared to our solar system, the TRAPPIST-1 planetary system has even more rocky planets in the habitable zone of the star than we do. Our solar system contains 2, Earth and Mars, and TRAPPIST-1 contains 7. The star around which this multiplanetary system is organized is an ultra-cold red dwarf, which is much cooler than the Sun, although it is more massive. It has a diameter of 11.5% that of the Sun, and a mass of 8%. It contains much more metal than the Sun, 109% more, according to scientists, and it can live 400 to 500 times longer, up to 4 to 5 trillion years. TRAPPIST-1a will certainly be one of the last remaining stars when the universe will be so old that the gas necessary for the formation of stars will be exhausted, and that our Sun will have disappeared for a long time. TRAPPIST-1 was discovered in 1999 by astronomer John Gizis and his colleagues. 16 years later, the Belgian telescope TRAPPIST discovered 3 planets orbiting this star. By crossing the information provided by the TRAPPIST telescope and those of other telescopes, 4 other planets were then discovered. These are the planets TRAPPIST-1d and TRAPPIST-1e, which are most likely to contain water in the liquid state, according to astronomers. They are neither the 2 closest nor the 2 farthest from their star. They are in fact the middle planets. TRAPPIST-1b and TRAPPIST-1c are closer to the star, so much so that Planet B orbits TRAPPIST-1a in 1.5 days and Planet C in 2.42 days, or 58 hours. TRAPPIST-1d is the least massive planet of the TRAPPIST-1 system. It has a mass equivalent to 30% that of the Earth. It is also the one which presents the weakest density and the gravity of surface. Its surface temperature is 9 degrees Celsius, or 48 degrees Fahrenheit. To give you an idea, the Earth's surface temperature is 15 degrees Celsius, or 59 degrees Fahrenheit on average. Separated from its star by 2.2% of the distance between the Earth and the Sun, it receives only 4.3% more sunlight than the Earth. TRAPPIST-1d orbits around TRAPPIST-1a in about 97 hours, or a little more than 4 days. Like TRAPPIST-1d, TRAPPIST-1e is located in the habitable zone of the multiplanetary system TRAPPIST-1. This planet has many points in common with the Earth. Its mass, its radius, its density, and its surface gravity are approximately similar. The data collected show that its composition should also be similar to that of the Earth. Its average temperature is minus 27.1 degrees Celsius, or minus 16 degrees Fahrenheit, a little colder than Earth's. But since the planet is in synchronous rotation, it would be warmer in the part illuminated by its star, and water would be in liquid state, and on the contrary, colder in the unilluminated part, where it would be in solid state. So yes, the TRAPPIST-1 system has habitable planets, but can we observe ocean planets there? According to a 2018 study by Amy Barr, Vera Dobos, and Laszlo Kiss, TRAPPIST-1d could be covered with an ocean, while the outer planets, i.e. TRAPPIST-1f, G, and H, would be icy planets. However, because we have not been able to observe the TRAPPIST-1 system live, these remain guesses. Other studies show that according to their characteristics, and in particular their atmosphere, other planets of the TRAPPIST-1 system could be watery worlds. The planets F, G, and H could thus have an oceanic surface and a large core. TRAPPIST-1f is probably rocky, with a massive envelope of water vapor at very high pressure and temperature. It could therefore be covered by a thick ocean with an atmosphere rich in abiotic oxygen. Attention, it is not because there would be oxygen that it would be an indication of life. The abiotic oxygen comes in reality from sulfur dioxide. TRAPPIST-1g, the sixth planet of the multiplanetary system, certainly harbors water, since it is less dense but more massive than the Earth. If it has no atmosphere, it is surely an icy planet. But if it has a thick water vapor atmosphere, it could be an ocean planet. As its orbit varies little, it should offer a rather stable climate rather favorable to the development of an aquatic life form. TRAPPIST-1h, the seventh planet of the TRAPPIST-1 planetary system, is even more distant from its star. It could harbor a subsurface oxygen heated by tides. There would thus be on this planet a strong activity of cryovolcanism, with erupting geysers, as on the moons Europa and Enceladus. Let's move a little farther away from Earth to examine a planet called K2-18b, which is located 124 light-years from us in the constellation Leo. This planet, discovered by the Kepler Space Observatory in 2015, orbits the red dwarf star K2-18 in 33 days and is located in its habitable zone. However, scientists believe it is unlikely to be habitable. K2-18b is 8 times more massive than the Earth. It is a super-Earth or mini-Neptune. In 2019, 2 independent studies concluded by cross-referencing data from the Kepler, Spitzer, and Hubble space telescopes that the atmosphere of this planet would contain significant amounts of water vapor. The equilibrium temperature of the planet is estimated to be about -8 degrees Celsius, or 17 degrees Fahrenheit, and it receives 94% of the stellar illumination that the Earth receives. Based on its size and density, it is unlikely to be composed entirely of iron and silicates, so it could be composed of hydrogen, helium, and ice water. In 2019, analyses of Hubble data by researchers from the University of Montreal and University College London examined the spectra of starlight passing through the planet's atmosphere during transits and concluded that K2-18b has a hydrogen-helium atmosphere with a high concentration of water vapor, between 20 and 50%. The water vapor could be high enough to form clouds. K2-18b was the first super-Earth discovered in the habitable zone of a star with a detected atmosphere. It was also the first discovery of water in an exoplanet located in the habitable zone. As a result of these observations, scenarios have been developed to determine possible models for this exoplanet. Several of these models admit that K2-18b could be an ocean world covered with liquid water and with temperature and pressure conditions similar to Earth. We will know more with the observations of the James Webb Telescope, launched at the end of 2021, and the Space Telescope Ariel, developed by the European Space Agency, which should be launched in 2028. The star Kepler-62 is much more distant than TRAPPIST-1 or even K2-18b. Located in the constellation Lyra, 1,200 light-years from Earth, it is an orange dwarf. At least 5 planets orbit it, including Kepler-62e and F, which are located in the star's habitable zone. In 2013, when they were discovered by the NASA Kepler Space Telescope, they were called the 2 most Earth-like planets ever discovered. Kepler-62e is a super-Earth, telluric like Earth, with a composition of iron and silicates. According to the hypothesis of scientists considered the most probable, it would contain an abundant quantity of water, in addition to its rocky core. According to a modeling study of this planet, published in the Astrophysical Journal, it is likely that the planet is entirely covered by an ocean. Kepler-62f is the farthest planet from the star Kepler-62, so it is located in the outer part of its habitable zone. It is 1.4 times larger than the Earth, so it is also a super-Earth. It receives as much solar energy as Mars, and the year lasts 262 days on this planet. Like Kepler-62e, it would be one of the first 2 viable candidate planets as a habitable zone ocean planet. A University of California study led by astrophysicist Omawa Shields, and published in 2016, estimated that the temperature of this planet would be compatible with the presence of liquid water. However, for Kepler-62f to indeed harbor oceans, it must meet a few criteria. The planet would have to have an atmosphere, 3 to 5 times thicker than Earth's, because its star heats less. This atmosphere, to maintain a temperature allowing the presence of water in a liquid state, should be composed largely of CO2. If, for example, the planet had an intense volcanic activity, it could maintain an atmosphere rich in carbon dioxide. And for it to be habitable, its atmosphere would have to be 3 to 5 times thicker than that of the Earth, as we have just seen. And in addition, the level of CO2 would have to be 2,500 times higher. What about the other planets in the Kepler-62 system? Astrophysicists have discovered 2 ocean planets, so they did not stop there. They investigated whether the other planets orbiting Kepler-62 could also be water worlds. Kepler-62b is the innermost planet in the multi-planetary system. It is about 30% larger in diameter than Earth and has an equilibrium temperature of 477 degrees Celsius, or 890 degrees Fahrenheit, which is slightly higher than that of Venus. No doubt, it is not an ocean planet. Kepler-62c is the second innermost planet after Planet B. It is about the size of Mars, but looks more like Mercury, the closest planet to the Sun in our solar system. It is therefore unlikely that this planet contains liquid water. Finally, Kepler-62d is not yet in the habitable zone, so it is too close to its star for water to remain in a liquid state. We end this journey with the planetary system Kepler-138. The star Kepler-138, or KOI 314, is a red dwarf star located in the Lyra constellation, 219 light-years from Earth. It is in the field of view of NASA's Kepler spacecraft, hence its name. In orbit around this star, 3 planets have been confirmed, and a 4th planet is likely. Kepler-138b is among the exoplanets whose size and mass have been measured, the one with the lowest mass. To give you an idea, the mass of Kepler-138b is similar to that of Mars. As for Kepler-138d, it has a very low density, so much so that it was long thought to be a gas dwarf planet, or mini-Neptune. A mini-Neptune is a planet whose mass is significantly less than that of Neptune, but which still shares some commonalities with this planet of our solar system. Mini-Neptunes have a thick atmosphere of hydrogen and helium over a deep mantle of water, ammonia, and other volatile compounds. If they did not have such a thick atmosphere, mini-Neptunes would actually be ocean planets. Recent studies from 2022 have shown that Kepler-138c and Kepler-138d are certainly watery worlds, with oceans 500 times deeper than those of Earth. They would also be warmer, with an atmosphere of hot water vapor. Let's go back for a moment to December 2022. Astronomers announced that they had identified the first true ocean planets, Kepler-138c and Kepler-138d. To reach this conclusion, astrophysicists compared the densities and masses of these planets with existing models And indeed, while these two planets are larger than the Earth, their density is nevertheless located between that of a rocky planet and that of a gas giant. To identify these oceanic worlds, astronomers use data from the Hubble and Spitzer space telescopes. The depth of the oceans of these two watery planets would be 500 times higher than the average of the terrestrial oceans, that is to say, a depth of at least 1,600 kilometers or 995 miles. Astrophysicists compared these two planets to Europa and Enceladus, except that Kepler 138c and Kepler 138d are larger and hotter than these oceanic moons, and instead of an icy surface, there would be large envelopes of water vapor. Kepler 138c and Kepler 138d constitute for astrophysicists the best evidence to date of the reality of oceanic planets, whose existence was theorized a long time ago. The oceans of these two planets would, however, be different from our terrestrial oceans. The available data show that they would be significantly warmer than our oceans, and that they would be under higher pressure. There may also be no clear boundary between the surface of the oceans and the atmosphere of Kepler 138c and Kepler 138d, which is certainly hot and composed of vapor. The temperature of this atmosphere is certainly above the boiling point of water. Under this hot atmosphere, there could be liquid water at high pressure, at depth, or in another phase like supercritical water. We have arrived at the end of this journey to the heart of the mysterious ocean planets. These aquatic worlds seem to come straight out of the imagination of a science fiction author. And yet, astrophysicists believe that it is more than likely that they really exist. What kind of creatures inhabit these extraterrestrial oceans? Are they microorganisms invisible to the naked eye? Huge prehistoric-looking creatures? Or ferocious creatures, like the Kraken of the fictional planet Mon Cala? Do these aquatic creatures have, as in our terrestrial oceans, a language to communicate between them? Do they inhabit the abysses of oceans more than 1,600 kilometers or more than 1,000 miles deep? Astrobiologists, astrophysicists, and astronomers are asking these questions and hope one day to be able to provide answers. The planet Earth was formed within the solar system. This solar system is a precious territory, more than 4 billion years old, and includes the Sun, the 8 known planets, as well as many small bodies of rock and ice, called asteroids and comets. The solar system is divided into several zones. The inner zone consists of the so-called telluric planets, Mercury, Venus, Mars, and of course the Earth. These 4 planets are rocky and metallic. Their size is relatively small. During their formation, the heat of the Sun has driven the gases from this area to concentrate dense elements. Beyond Mars, there is a belt of asteroids. These are millions of blocks of rock, waste products of the formation of planets. From this asteroid belt, we enter the domain of the giant planets, Jupiter, Saturn, Uranus, and Neptune. In this external zone of the solar system, the lower temperature during the formation of our solar system allowed the existence of volatile elements. The planets are larger in size than the terrestrial planets and are composed of light elements such as hydrogen and helium. The formation of the solar system took place after a nebula gradually collapsed on itself, following the explosion of a supernova. The primitive nebula flattened under the effect of its rotation. The central part of the nebula heated up and formed a protosun. Dust rich in carbon, ice, metals, and minerals have then clumped together. This phenomenon is called accretion. These blocks met until they formed protoplanets, and then a few million years later, the planets in their current size. If we start from the Sun, the Earth is the planet that is in third position. It is the only planet in the solar system with liquid water on its surface. 70% of the globe is covered with oceans several tens of kilometers deep. Its atmosphere is composed mainly of nitrogen and oxygen. The conditions found on this terrestrial planet have allowed life to develop and evolve in a complex manner. Currently, no other planet is known to harbor life. The Earth has always been subject to vigorous volcanic activity. It has a diameter of almost 13,000 kilometers, or about 8,000 miles. The Earth has a very particular composition, since to date is the only telluric planet that has 4 distinct layers, including a core in 2 parts. On the outside, the Earth's crust is 5 to 80 kilometers, or 3 to 50 miles thick. It is mostly composed of rocks derived from volcanism. Under the crust is the mantle. Although it is hot and malleable, it remains solid and extends to almost 3,000 kilometers, or 1,900 miles deep. It is composed of minerals such as oxygen, silicon, iron, and magnesium. At the center of the Earth is the core, which is divided into 2 parts. The outer core is composed of metallic elements. Its liquid structure is traversed by electric currents that create the magnetic field. The solid inner core, composed of iron and nickel, is subject to a phenomenal pressure and a temperature reaching 6,000 degrees Celsius, or 10,800 degrees Fahrenheit. The Earth's atmosphere contains very little carbon dioxide because it dissolves in the oceans. Nitrogen dominates our atmosphere, followed by oxygen, argon, some other gases, and water vapor. The gases present are transparent, whereas water vapor is visible when it condenses into a cloud. The latter can cover up to 60% of the Earth's surface. In the solar system, the atmosphere most similar to that of the Earth is that of Titan, a moon of Saturn. The atmosphere of Mars is 100 times less dense than that of the Earth, and that of Venus is 100 times more dense. Ozone is a molecule that contains 3 oxygen atoms. The gas present in the atmosphere absorbs the harmful ultraviolet rays of the sun, allowing life to thrive on the surface. The Earth is different from other planets because of its geology and its complex climate. Another of its characteristics is that its crust is divided into tectonic plates that are mobile in relation to each other. The other telluric planets are called monoplate because they have only one crust. This division of the crust into tectonic plates gives rise to telluric movements. If seen from the sky, the Earth looks like a blue planet, it is because 2/3 of its surface is covered by oceans, and that erosion has erased the craters of asteroids and comets that may have hit its surface. Next to the Earth is the Moon, its satellite. It is the 5th largest satellite and the only moon in the solar system to be called Moon. The Moon is devoid of atmosphere and life. There has never been liquid water on the Moon. Meteorite impact craters and ancient volcanic eruptions shape its surface. Seen from Earth, the Moon offers two types of very contrasting terrain, with dark and light areas. The latter, called continents, are massive areas riddled with asteroid impact craters that formed in the first billion years of the solar system's history. The dark areas are called seas. They are vast plains of lava, emitted by volcanoes. The Moon exerts a significant attraction on the Earth, although it has a weak gravity field and is rather far from the planet. Combined with the attraction of the Sun, the influence of the Moon causes the tides, which result in the rise and fall of the waters of the oceans. During a full or new moon, when the Moon, the Earth, and the Sun are aligned, the forces of gravity add up to create the high tides. The high tides are then very high, and the low tides very low. When only a quarter moon appears, the Earth to Moon and Earth to Sun axes are at right angles, and the forces of gravity partially cancel each other out. The tides, called neap tides, are then reduced. The one who reigns supreme in this gigantic domain, and without whom the Earth, and consequently man, would be nothing, is the Sun. This giant ball of hydrogen and helium contains 99.9% of the total mass of the solar system. The Sun is a star. Although it seems huge to us, it is medium-sized with a diameter of almost 1,400,000 kilometers, or 870,000 miles. The Sun is in the middle of its life cycle, since it has already used up between 35 and 45% of its hydrogen reserves. In about 6 billion years, the hydrogen will be totally consumed, and the Sun will start to expand. It will then become a subgiant star, brighter but less hot. A billion years later, the star will become a red giant, growing even larger. It will then eject its outer layers into space until its core curls up into a white dwarf. It is within its core, the central region of the Sun, that nuclear reactions occur. The energy released rises to the surface and escapes in the form of light and radiation. It is thanks to this same energy that life on Earth is possible. The atmosphere acts as a shield. It allows the solar energy to penetrate and prevents the heat from escaping, while preventing the dangerous solar radiation from reaching the planet. This effect is called the greenhouse effect. The atmosphere keeps us comfortably warm day and night. Human beings are entirely dependent on the Sun, which is involved in the entire life cycle. The star heats the land, oceans, and air. When the water evaporates, clouds form. Within these clouds, water droplets are formed as the water vapor cools. They will then fall back down as rain. Humans, animals, and plants benefit from this water. Plants also use sunlight for photosynthesis. They convert carbon dioxide and water into carbohydrates necessary for their development. In return, they release the oxygen that living things need to breathe. Mercury is the closest planet to the Sun. It looks like a ball of iron surrounded by a thin rocky mantle. Its surface is, like that of the Moon, covered with impact craters. The Caloris Basin is one of the best-known impacts, so large that it could contain almost the whole of Texas. Apart from the craters and plains, compression faults appear, which form cliffs, and which can reach 3 kilometers or 2 miles in height. Having no atmosphere or liquid water, Mercury's only erosion comes from the impact of meteorites, asteroids, and comets. Mercury has no moon. Its proximity to the Sun results in an average ground temperature of 430 degrees Celsius, or 800 degrees Fahrenheit. It also experiences great temperature contrasts, since when its hemisphere is plunged into the night, the temperature decreases to about minus 200 degrees Celsius, or minus 328 degrees Fahrenheit. It is smaller than the Earth, but so dense that it certainly has an important iron core. Venus is the closest planet to Earth. It is about the same size as Earth, but is far from being its twin. A thick atmosphere of carbon dioxide covered with clouds of sulfuric acid obscures its surface. The pressure exerted on the ground is equivalent to that of a deep sea of 900 meters or 3,000 feet. While it is farther from the Sun than Mercury, the average ground temperature of Venus is warmer and reaches up to 490 degrees Celsius, or 914 degrees Fahrenheit. The surface of Venus is covered with volcanic edifices such as pancake domes, which are circular and flattened reliefs formed by a gas-rich lava. This lava spreads like a pancake batter, then solidifies and breaks. The highest volcano on Venus is Mont Mons, which rises to 8,000 meters or 26,000 feet. Its lava flows can reach hundreds of miles and miles in length. Mars comes in fourth from the Sun. Its diameter of just over 6,700 kilometers or 4,200 miles is twice as small as Earth's. It has a thin atmosphere containing mainly carbon dioxide. Its unstable climate leads to the formation of ice caps. Many extinct volcanoes culminate on its surface, including Olympus Mons. It is one of the highest known landforms in the solar system, with a peak reaching over 21,000 meters, or 69,000 feet. It seems that liquid water, in the form of real seas, covered its surface in the distant past. The first geological hours of Mars were marked by meteoric bombardment and strong volcanism. The ancient craters thus eroded by water gave birth to rivers. There was then at that time a hydrodynamic cycle. The climate should be mild and stable, thanks to the presence of oceans allowing the water cycle. Nevertheless, the weak mass of the planet could not allow to retain the gases of its atmosphere, and the cycle of the water dissipated. The water would then have evaporated and been absorbed within porous rocks. The density of Mars is lower than that of the Earth, because its smaller mass compresses its deep layers less. It is called a red planet because of a thin layer of red dust composed of iron oxide that covers its surface. Most of the southern hemisphere is covered by high plateaus riddled with impact craters. In the north, there are basins and large volcanoes. Mars has two moons, Phobos and Deimos. These are asteroids that have been captured by its gravity field. They are riddled with craters and have irregular shapes. Both are small, with modest diameters of 27 kilometers or 17 miles for Phobos, and 15 kilometers or 9 miles for Deimos. The distance between Deimos and Mars is such that it is in synchronous orbit with the planet. The Moon is always at the vertical of the same place. A cluster of asteroids circulates between the orbits of Mars and Jupiter. Irregularly shaped, they can reach sizes ranging from a small stone to a mini planet. The largest of them, Ceres, has a diameter of about 950 kilometers or 590 miles. It was even classified as a dwarf planet. Asteroids are composed of minerals, metal, or carbon. They are riddled with impact craters. They could not aggregate to form a planet because the gravity field of Jupiter disrupted and scattered the blocks. These rocky bodies orbit the Sun, but their small size prevents them from being classified as planets. The majority of asteroids are located in the main belt. Its thickness measures between 100 and 300 million kilometers, or between 60 and 190 million miles. Asteroids are classified into 3 distinct families according to their chemical composition and morphological characteristics. We find the asteroids of type C, called carbonaceous, the asteroids of type S, rich in silica, and the asteroids of type M, said metallic. About 75% of them are C-type asteroids. They are lodged in the most distant regions of the asteroid belt and are the least luminous. Can these lumps floating in the sky be made to crash into the Earth and become a threat to life? Some fragments of asteroids can head towards the Earth and collide with it. They are called meteoroids. If one of these meteoroids enters the Earth's atmosphere at high speed, the friction creates heat so great that it burns the meteoroid to ashes and produces a trail of light across the sky. If the meteoroid does not burn up completely, the remaining piece can then touch the Earth. It is then called a meteorite. An impact with a large meteorite could obviously leave obvious signs on the surface of the Earth and cause dramatic consequences for life. Jupiter is the largest planet in the solar system. It could contain all the other planets in its interior. Its composition is almost entirely gaseous and consists mainly of hydrogen and helium. Jupiter is more like a star than a real planet. After Venus, Jupiter is the most luminous planet. It has a compact core of rock and ice, formed of compressed hydrogen and helium. This core represents about 5% of its mass. It is enveloped by volatile elements. Jupiter is spectacular. It has no solid surface and a dynamic atmosphere. From the Earth, we can observe an alternation of dark belts and clear areas. This banded arrangement is due to its rapid rotation, which stretches the disturbances around the globe and confines the clouds of its atmosphere in a set of parallel lines. In the middle of these bands, cyclones and anticyclones are present. The most famous of them is the Great Red Spot. It owes its bright color to molecules containing phosphorus. This anticyclone is larger than the Earth. The Great Red Spot is constantly shrinking from 40,000 kilometers, or 25,000 miles, in 1930 to 16,000 kilometers, or 10,000 miles long, in 2014, and would disappear within 70 years. Jupiter has a ring system that remains dark and is only visible when it is in the planet's shadow. The planet is not only distinguished by its size, it also has the largest number of moons. To date, 95 are known. Saturn is the second largest planet in the solar system. But what makes it famous are the rings that surround it. With the help of a small amateur telescope, it is possible to observe them from Earth. Saturn's rings are a world apart. They are composed of many ice particles acting as an independent satellite. Some of them can reach the size of a house. The particles in these rings are shiny, coated, or composed of highly reflective ice. Saturn's rings are brighter than those of other planets and reflect up to 60% of sunlight. they are flattened. Although they measure 280,000 kilometers, or 170,000 miles in diameter, their thickness does not exceed a few meters or feet on average. Saturn has a solid core of rock and ice. Its atmosphere contains mainly hydrogen and helium. The clouds are deeply buried, and their color, blurred by layers of haze, gives the planet a livid hue. One of the characteristics of Saturn is that it has a flattened shape at the pole. This is due to its extremely fast rotation on itself, of less than 10 hours 30 for a complete turn. Saturn, imposing in terms of mass and gravity field, has captured a large number of asteroids that have become its moons. 83 known satellites are attributed to it today. Among them, Titan has a diameter of more than 5,000 kilometers, or 3,100 miles, and is the second largest moon in the solar system. Titan is surrounded by a thick layer of nitrogen. Being quite far from the Sun, the temperature on its surface is extremely low. By continuing to move away from the Sun, we can observe in the sky a ball with blue-green reflections. It is the planet Uranus. It is the third largest planet. Its diameter is 4 times that of the Earth. Its particular color is due to the presence of methane. No details of its atmosphere are visible, neither cloud bands nor cyclonic formations. Unlike Jupiter and Saturn, which are considered as gas giants, Uranus is similar to an ice giant. It is much denser, and its internal layers must contain elements heavier than hydrogen, like ice. Uranus goes around the Sun in a little more than 84 years. This situation gives it strange seasons. This is also explained by the fact that its rotation axis is almost lying in the plane of its orbit. Long periods of sunlight follow long periods of darkness. During the winter solstice, the northern hemisphere is plunged in the night for 21 years. The planet Uranus has rings. 13 are currently known. 11 located in the inner system and 2 in the outer system. Their capacity to reflect light is extremely low. They are therefore difficult to see. These rings are composed of dust particles with dimensions of the order of a centimeter. They could have been formed by the fragmentation of a small moon after a collision with a meteorite. Uranus has so far 27 known moons. 5 of them are large. The others are only a few tens of kilometers in diameter. The largest, Titania, measures 1,580 kilometers in diameter. But the strangest of the moons encountered so far is Miranda, the 5th satellite of Uranus in size. Its surface shows complex and extraordinary geological formations. One could compare it to a giant puzzle, as if this moon had been torn apart and then put back together. It could be that Miranda was smashed during a collision, and that the pieces in orbit around Uranus were then reassembled until the moon was reconstituted. Neptune is a gas planet. Unlike Jupiter and Saturn, its solid core is larger than its total mass. Neptune's atmosphere is characterized by strong winds of over 2,000 kilometers per hour, or 1,200 miles per hour, and large cyclonic formations that persist for long periods. The most visible large dark spot is as large as the Earth. The last planet in the solar system glows with a beautiful azure color. This hue is explained by the presence of methane in its atmosphere, which absorbs red radiation and lets only blue radiation filter through. Its atmosphere is composed, in addition to methane, of hydrogen and helium.
Neptune has an important internal heat source, since it emits a quantity of energy equivalent to almost 3 times that received from the Sun. 5 rings surround Neptune. They are composed of ice, covered with a large carbonaceous dust, and remain very difficult to detect. Because of its remote distance from the Sun, the number of Neptune's moons remains poorly known. Triton is the largest of Neptune's satellites known to date. This moon has canyons, craters, peaks, and very long fissures, forming a most amazing landscape. It also has very strange volcanoes on its surface. It seems that Triton's volcanoes look like geysers that emit jets of gas and dark carbon compounds from underground. Pluto was considered the 9th planet in the solar system. In 2006, it was reclassified as a dwarf planet. Dwarf planets are considered to be stars orbiting a star, more or less spherical, and often found in the vicinity of many other large objects such as asteroids, comets, or other dwarf planets. As their name indicates, these planets are small. They cannot exert the gravitational forces necessary to attract and hold objects in their orbit. With its 2,300 kilometers, or 1,430 miles in diameter, Pluto is smaller than the Moon, and yet the largest and second most massive dwarf planet. Its essentially rocky core occupies the majority of the planet's volume. Its surface consists of plains and mountains, covered with a thick layer of ice, probably water, mixed with traces of methane, nitrogen, and carbon monoxide. It takes almost 250 years for Pluto to go around the Sun. Beyond Pluto, a vast region of comets opens up. Comets are visible to us as they approach the Sun, as they develop a glowing tail. But billions of invisible comets stay at the edge of the solar system. Comets are classified into 2 families: long-period comets that circle the Sun in more than 200 years, and short-period comets. The long-period comets have orbits inclined with respect to the circulation plane of the planets. Their trajectories are varied, suggesting that they belong to a vast spherical cloud that envelops the solar system like a cocoon. The Kuiper Belt is the source of short-period comets. It is located around 30 astronomical units and extends to hundreds of astronomical units. It is home to hundreds of icy objects, some of which reach the size of large asteroids. Extending over a few tens of billions of kilometers, it is 1,000 times smaller than the Oort cloud. The Oort cloud is the reservoir of long-period comets. It extends over distances between 30,000 and 100,000 astronomical units. This spherical cloud is hypothetical, since it could not be observed directly, as it is beyond the reach of our instruments. The knowledge of its existence is based on the analysis of the orbits of several comets. In 1932, the first astronomer postulated that comets orbiting for long periods of time came from a large cloud located beyond the limits of the solar system. About 20 years later, another astronomer put forward a theory according to which meteorites could not have formed in their current orbit because of the astronomical phenomena that govern them. He deduced that they must be stored in a large cloud, the Oort cloud. A comet that passes near the Sun loses part of its mass, volatilized into gas and dust. One might think that in a few tens of thousands of years, a comet should have completely melted. However, the solar system has always been full of comets. there is in fact a vast reservoir of comets hibernating around the Sun. As the Sun moves through the Milky Way, it is subject to tidal forces as it passes near other stars. Comets can then be dislodged from the Oort cloud and directed towards the interior of the solar system. Comets are bodies composed of a head, which includes a nucleus surrounded by a luminous hair of gas. The nucleus of the comet presents different colorations, varying from black to gray through red. The nucleus is composed of common silicate and molecules composed of carbon, oxygen, nitrogen, and hydrogen. When it is far from the Sun, the comet is invisible, like many other small celestial bodies. As the comet approaches the inner regions of the solar system, the heat produced sublimates some of the ice present in the nucleus, which, mixed with other gases, forms the hair and the tail. As the comet passes through the solar system, the material of which the short-period comet is composed is depleted and transforms it into a tiny body among others. It happens that the Earth, during its own rotation around the Sun, crosses the dust or gases that have been left behind by a comet. These materials, while crossing our atmosphere, create magnificent swarms of meteors that are called shooting stars. During the formation of the comet's hair, carbon dioxide and carbon monoxide first evaporate. Then it is the turn of the ice. The emitted gas disperses in space and is replaced by new matter. The vaporization takes place only on the side facing the Sun, where the comet is active. The material emitted from the nucleus can spread out into space for hundreds of thousands of miles and miles. When the comet shines and becomes visible, its tail can be seen, which comes from the gases in the hair. A comet has in most cases at least two tails. One is composed of ionized gas and the other of dust. The latter are not always visible. The gas tail is bluish in color because of the presence of carbon monoxide. It can measure up to several 100 million kilometers and miles. They are always straight and consist of structure, node, and condensation. The sudden separation of the tail from its hair is one of the most spectacular phenomena. Man, from his planet Earth, seems infinitely small when placed on the scale of the solar system, and yet the universe is far from stopping there. The solar system is located in a galaxy called the Milky Way. It is a huge disk of stars in motion that measures nearly 1,000 million billion kilometers in diameter. Along its diameter, one could line up 130 million solar systems. And yet, the Milky Way is one galaxy among many. Galaxies are gigantic clusters of stars that can extend over hundreds of thousands of light years. Presenting a wide variety of sizes and shapes, galaxies are classified into two main families: elliptical and spiral galaxies. Spiral galaxies are further subdivided into simple spiral, barred spiral, and lenticular galaxies. Elliptical galaxies are the most massive. The spiral and lenticular galaxies can reach diameters similar to the large elliptical, but are less massive because they are flattened. Spiral galaxies represent 60% of all cases, and 30% are elliptical. The best known remain the spiral galaxies. Among them, we find barred spiral galaxies, which have a thick bar of stars crossing their heart and extending by an arm at each end, and normal spiral galaxies, which see their arms emerging directly from the heart of the galaxy. Spiral galaxies are flattened like a disk with a central bulge of old red stars. The disk at the periphery contains clouds of gas and dust that will serve to form new stars. Spiral galaxies are rotating, resulting in density waves that compress the gas and dust to form bright blue stars that illuminate their arms. A spherical halo of globular clusters containing up to 1 million old red stars surrounds spiral galaxies. The so-called elliptical galaxies have a slightly flattened oval shape. They have 3 axes of different lengths. The lenticular galaxies have, as for them, a lens shape. They remind both spiral galaxies and elliptical galaxies. They have, like spiral galaxies, a disk with a central bulge that houses clouds of gas and dust. They differ by the absence of spiral structure. They do not have young blue stars and host only old red stars. There are 2 theories explaining how galaxies are formed. According to the first theory, galaxies form from huge clouds of gas that collapsed in on themselves by gravity. The second theory suggests that galaxies would have assembled from smaller objects. Both processes could have been at work when the galaxies formed more than 10 billion years ago. Just 1 or 2 billion years after the Big Bang, the universe then consisted of a vast expanse of hydrogen and helium. Some parts of this universe, denser than others, attracted matter, thanks to their gravitational forces. These regions individualized into huge clouds that would later become future galaxies. These different clouds were brought to meet and thus form even denser sets. During the collisions, shock waves stirred up the gas and caused it to collapse into stars and star clusters. It seems that in earlier times, the universe contained a higher proportion of spiral galaxies than today. This change in the appearance of the universe is due to repeated collisions between galaxies. Indeed, when spiral galaxies collide, they merge to give elliptical galaxies. The merger thus explains their large size and why they contain so little gas and so many red stars. From our human eyes in the night sky, the Milky Way appears as a whitish molten band crossing the celestial sphere. It takes the form of a ring, of which only a part is revealed. From the Earth, its brightness is weak and diffuse. In reality, we can only see the side of the galactic disk, composed of an endless string of stars that the human eye is unable to distinguish. Many stars, planets, and nebulae populate the Milky Way. A star is a ball of ionized gas made up primarily of hydrogen and helium, the 2 most abundant elements in the universe. Stars tend to collapse under their own weight. This is called gravitational contraction. The nuclear reactions that occur within the star also exert pressure from the inside out. The balance between these 2 forces gives stars their own dimension. The core of the star is subjected to high temperature and pressure. The hydrogen nuclei collide and form helium nuclei. Thanks to these reactions, a star can shine for billions of years. Its surface temperature will depend on its color. Our Sun is a yellow star of average size. Stars are born in molecular clouds. These are large areas of gas inside which some regions are denser than others and attract by gravity the gases present around. A globule is then formed and contracts until it becomes a protostar. The contraction causes an increase of the rotation, as well as an increase of the temperature and the pressure. The thermonuclear reactions start. The star is born. The north and south celestial poles are the extension of the Earth's axis to infinity and are the only two immobile points in the sky. The North Star indicates almost exactly the North Pole. It is not very bright, since it is only the 48th star in the sky in order of brightness, but it is one of the most important landmarks, since it does not move and always indicates north. Thanks to it, it is possible for us to orient ourselves at night from Earth without a compass or GPS. 200 billion stars populate the Milky Way, and only 3,000 of them are visible to the naked eye. The closest star system to us is Alpha Centauri. It is a complex system composed of 3 stars. The 2 largest form a double star, located 4.37 light-years from the solar system. Their size and color resemble those of the Sun. They are accompanied by Proxima Centauri. It is a tiny star, a brown dwarf, measuring 1.5 times the size of Jupiter. Proxima Centauri is a little closer to us than the main components of Alpha Centauri, since it is 4.24 light-years away. From Earth, Alpha Centauri shines with an impressive brightness. It is the 3rd brightest star in the sky. With the help of a telescope, the 2 main components of Alpha Centauri form a beautiful double star. Several types of stars populate the Milky Way: binaries, multiples, and variables. Almost half of the stars in our galaxy are binaries. Binary and multiple stars are stars that orbit a common center of gravity and are bound together by gravitational attraction. Binary stars form within the same cloud of matter, which during its collapse splits into 2 pockets. Some clouds split into multiple parts and can group up to 6 stars. A variable star sees its brightness change for several reasons. When a star passes in front of another, for example, it will modulate the amount of light we receive. The periodic pulsations of the star's surface can also change its brightness. The light emitted is a function of the surface of the star. Stars at the end of their life expand and contract. Stars can undergo unpredictable variations in brightness due to gas eruptions or other cataclysmic phenomena. Chelyabinsk is an eclipsing binary star, which is very surprising. It consists of 2 stars so close to each other that they exchange matter and deform each other. The larger of the 2 loses the equivalent of the mass of the Sun every 50,000 years. Chelyabinsk is located in the constellation of Lyra. If our planet were positioned near this infernal stellar couple, the inhabitants would see huge protuberances tear away from the larger one to wrap around the smaller one. But from the Earth, we only notice the brightness of Chelyabinsk diminished as soon as the smaller star passes in front of the larger one. A set of neighboring stars can sometimes present a figure on the celestial sphere. These are the constellations. From the Earth, man can observe different figures drawn by stars like Orion, the Big Dipper, or the Southern Cross. The stars have their own movement, but they are so far away from us that they seem fixed. Their position will change gradually to the point that our familiar constellations will become totally unrecognizable in the distant future. The Big Dipper is the most famous constellation in the Northern Hemisphere. It is close enough to the celestial pole, where the North Star is located, that it never disappears below the horizon, whatever the time of night or the season. The 7 brightest stars of the Big Dipper form a distinctive saucepan shape. Most of its stars are less than 100 light-years away and belong to an open cluster that is almost completely dislocated. Many legends have been associated with this constellation. According to Greek mythology, it represents the nymph Callisto, changed into a bear by Hera, the wife of Zeus, after her husband fell in love with her. Zeus would then have raised the bear to the heavens to place it near the sun, Arcus, whom he had with Callisto, and who was also transformed into a little bear. The universe favoring groupings, the stars are often binary or multiple. But on a larger scale, larger groupings of stars are formed as open or globular star clusters. Globular clusters can contain from 100,000 to more than 1 million stars. They are similar to tiny elliptical galaxies. They contain old stars of red color, while the open clusters are populated by young blue stars. Within these clusters, collisions are frequent, leading to the formation of new stars called blue wanderers. Globular clusters orbit the center of the galaxy, and together form a spherical halo. The Milky Way contains nearly 150 globular clusters in its halo. One of the brightest clusters is Omega of the Centaurus. It peaks high in the southern sky in March and April. To the naked eye, it looks more like a spot than a star. Through a telescope, we can see that many small stars dot its surface. Omega Centauri contains nearly 10 million stars over 10 billion years old. It is the largest globular cluster in the galaxy. This cluster could be the remnant of a small galaxy that was swallowed by our Milky Way. Nebulae are interstellar clouds that contain the raw material to make new stars. These clouds come in a variety of sizes and colors. The smallest nebulae are called globules. Their diameter is of the order of a light-year, and they look like dense and dark spots. Large molecular clouds contain enough material to make tens of millions of stars. All clouds are composed of gas and helium, as well as grains of carbon and silicon dust. When a new star forms in an interstellar cloud, the light ionizes the gases and creates luminescence. Some clouds do not emit their own light. They reflect or scatter the light of nearby stars and nebulae. The Orion Nebula is the closest to Earth. It shines according to a phenomenon of fluorescence. The atoms of the gas are stimulated by the ultraviolet radiation of bright stars, which leads them to diffuse light in turn. In this nebula, many stars and planetary disks are forming. It is easily observable from Earth simply with binoculars. This nebula looks like a small cloud in which the central region appears greenish. The Milky Way is a spiral galaxy. It consists of a flat main body in the form of a disk with a diameter of more than 100,000 light-years. This disk contains the vast majority of stars. It contains curved structures from the core that extend to the borders of the galaxy. These are the spiral arms. Inside these arms, the matter reaches a high density, and clouds of gas and interstellar dust give birth to new stars. In the center of the flattened disk, we find the galactic nucleus which shelters the halo, a shell populated by the oldest stars and globular clusters, representing the ancient stellar systems of our galaxy. Globular clusters have an extremely high density and are extraordinary objects that we can contemplate through a telescope from Earth. "27,000 light-years away from the heart of the galaxy, we find the Sun, our star. It is located on the periphery, 2/3 of the galactic radius from the center. We, the inhabitants of the Earth, travel in space, following the movements of our planet, with the whole solar system within the Milky Way. These movements are imperceptible, but they are similar to a crazy race of 600 kilometers per second, or 370 miles per second. The Milky Way rotates on itself in about 240 million years. The Sun orbits around its center at a speed of about 220 kilometers per second, or 136 miles per second. The starry sky that illuminated the Earth at the time of the dinosaurs was therefore very different from the sky we can observe today. During this time, the Sun has gone through at least 1/3 of its revolution. It moves in space with its own motion that is superimposed on the revolution around the galactic center. The stars are subject to the local attraction exerted by the nearby stars. They have their own motion and move through the galaxy. The constellations that we observe did not exist at that time, and they will not exist in the future. One of the particularities of the Milky Way and of any other spiral galaxy is that its rotation occurs in a differentiated way. The central stars and celestial objects have a shorter period of revolution than the more distant stars and objects. The objects that populate the Milky Way, such as open and globular clusters or nebulae, move across the sky. The movement of globular clusters is particularly remarkable. These dense clusters are composed of hundreds of thousands of old stars that inhabit a spherical region around the nucleus and disk of the galaxy. They are like satellites and revolve around the galactic center in elliptical orbits more elongated and inclined than the disk. Their movement is very fast, about 200 kilometers per second, or 125 miles per second, and they regularly cross the disk. Thanks to their density, they remain stable. However, the interaction with the plane of the Milky Way leads to their disintegration. The open clusters have a different motion. Containing only a few hundred or thousands of stars, these clusters break up in the spiral arms. Their stars being less thick than those of globular clusters, they tend to disintegrate over tens of millions of years. Therefore, globular clusters can reach a lifetime of more than 10 billion years, while open clusters are younger. A large band of dust called the Great Rift splits the Milky Way in two. Originally, our galaxy was made up of stars and hydrogen clouds, and we could see through them very well. Since then, countless stellar explosions have released dust that has accumulated inside, completely changing its appearance. When we look towards the interior of the galaxy, the Great Rift is positioned between the constellation of Cygnus and the southern constellation of Centaurus. All spiral galaxies are now crossed by such dust bands. The Milky Way belongs to a group of about 60 galaxies called the Local Group. The Milky Way is not the only galaxy in the universe. Many small, faint nebulae in the night sky are also galaxies. They are distant from the Milky Way. Galaxies are not uniformly distributed in the universe. They form groups more or less large. Large galaxies are usually accompanied by dwarf satellite galaxies. There are two that can be seen with the naked eye from Earth. They appear as nebulae. They are the Magellanic Clouds. 24 other dwarf galaxies of low brightness are next to them. A little further away, we find the great galaxy of Andromeda, itself surrounded by two other, relatively large neighbors, and many small satellite galaxies. The Milky Way, accompanied by the Andromeda Galaxy and the Triangulum Galaxy, forms the Local Group with many other smaller galaxies. Counting also the dwarf galaxies, the Local Group includes more than 50 members. The three large spiral galaxies that are the Milky Way, the Andromeda Galaxy and the Triangulum Galaxy, are accompanied by dozens of smaller galaxies. The satellite galaxies are those present in greater numbers. They swarm around the large spiral galaxies like mosquitoes around a lamp. These satellite galaxies are discrete agglomerations of several million stars of a few thousand light-years in diameter. The Triangulum Galaxy has no satellite galaxies, while the Milky Way and the Andromeda Galaxy are surrounded by many. They probably grew by swallowing small satellite galaxies. This process is still going on today. For example, the Sagittarius dwarf galaxy has been stretched by the tidal forces of the Milky Way and will eventually be swallowed by it. The Large Magellanic Cloud is about 15,000 light-years in diameter. It is composed of a few billion stars and is located 163,000 light-years from Earth. Due to its high content of gas and interstellar dust, the level of star formation activity is very high. The largest star-forming region of the Large Magellanic Cloud is the Tarantula Nebula. It is so bright that if it were located at the same distance as the Orion Nebula, it would never be dark on Earth. The Large Magellanic Cloud contains dozens of globular clusters, hundreds of open stellar clusters and planetary nebulae. It contains many more heavy elements than the Milky Way. These have been created over time by nuclear fusion reactions within the stars themselves, indicating that the Magellanic Clouds are younger than the Milky Way. The brightness of the Magellanic Clouds is incomparable to that of the Milky Way. From the southern hemisphere, and in the absence of light pollution, they appear distinctly to the naked eye. The small Magellanic Cloud is located further away than its big brother, 200,000 light-years from Earth. It contains fewer stars, only 3 billion. It is less bright in the night sky, but it is still recognizable to the naked eye. The small Magellanic Cloud contains a large number of Cepheids. These are stars whose brightness varies over a period of days or weeks. The Andromeda Galaxy is located 2.5 million light-years from Earth. From the northern hemisphere, on a moonless autumn night and on a clear day, the Andromeda Galaxy appears as a diffuse patch of light. It is one of the most distant objects in the universe that can be seen without the aid of optical instruments. The Andromeda Galaxy contains about 1 trillion stars, at least twice as many as the Milky Way. It is larger than the latter. It is the largest galaxy in the local group. However, it seems to contain fewer star-forming regions. The Andromeda Galaxy was born 5.5 billion years ago from the collision and merger of 2 smaller galaxies. The Triangle Galaxy owes its name to the constellation in which it is located. This spiral galaxy is located almost 3 million light-years from Earth. It has a low brightness. Nevertheless, under extremely favorable conditions, it is possible to see it with the naked eye from Earth. The Triangulum Galaxy is the smallest of the 3 large galaxies in the local group. It is half the size of the Milky Way, contains about 40 billion stars, and is about 50,000 light-years in diameter. The Triangulum Galaxy is home to a large number of star-forming regions, including the largest, NGC 604. This magnificent nebula in emission surpasses the brightness of Venus. Its gas is ionized by a cluster of massive stars at its heart. Distributed in at least 2 clusters, there are about 200 stars with masses ranging from 15 to 60 solar masses. The diameter of the Triangle Nebula reaches about 1,500 light-years. In about 4 billion years, the local group will see the Milky Way and the Andromeda Galaxy collide. 2 billion years later, they will merge to form a single giant elliptical galaxy. The Sun and its planets could be catapulted into space because of gravitational disturbances. The Triangulum Galaxy, meanwhile, may collide with the Milky Way a little earlier. It may end up orbiting the giant elliptical galaxy that will form during the collision between the Milky Way and the Andromeda Galaxy. Laniakea is a Hawaiian word meaning immense celestial horizon or immeasurable paradise. It is a supercluster of galaxies that includes, among others, the Virgo supercluster, which hosts the Milky Way, and thus our planet Earth. Our local group forms with other galaxies a superstructure in a quasi-central position within the Virgo cluster. The latter is like a vast and flat expanse, including a small central bulge that is called local supercluster. The local cluster represents only one of the 6 million superclusters in the observable universe. Laniakea consists of 3 superclusters: the Virgo supercluster, of which we are a part, the Hydra-Centaur supercluster, in which the Great Attractor is located, and finally, the Peacock-Indian supercluster. As in most galactic clusters, the space between the different galaxies is not really empty. It is filled with rarefied gas, mainly hydrogen and helium, at a temperature of nearly 30 million degrees Celsius, or 54 million degrees Fahrenheit. Laniakea extends over 500 million light-years. This supercluster contains more than 100,000 galaxies. The mass of Laniakea is estimated at about 100 million billion times that of the Sun. Each of the 100,000 large galaxies like ours has an average of 100 billion stars and a million dwarf galaxies. The local group is located in the Virgo supercluster. The Hydra Centaurus supercluster is the closest neighbor of the Virgo supercluster. It is actually two superclusters, the Hydra and the Centaur, which are gravitationally connected. The Peacock Indian supercluster contains three main clusters: a Bell 3656, a Bell 3698, and a Bell 3742. At the heart of the Laniakea supercluster is the Great Attractor. This gravitational anomaly in intergalactic space demonstrates the existence of a local concentration of mass equivalent to tens of thousands of times the mass of the Milky Way. Our galaxy and all those in our supercluster are heading towards the Great Attractor. If one imagines a picture from the sky that represents the distribution of all the superclusters in the observable universe, the Milky Way is much too small to be visualized. Proportionally, the solar system, the Earth, and man can only be imagined. We are a tiny part of a speck of dust in this vast ocean. This vast ocean in question represents, in our eyes, the so-called observable universe. The further man looks into space, the further he looks into the past. The speed of light is not infinite, but the finite speed of light, combined with the finite age of the universe, delimits an impassable border between which we cannot see. This is the cosmological horizon. Even with the best telescope, everything beyond this limit remains undetectable. Light needs time to reach us, but the possible travel time is limited since the universe is 13.8 billion years old. Thus, the light from a galaxy located 20 billion light-years away from us has not yet had enough time to reach the Earth. It is beyond our cosmological horizon. It is comparable to the horizon that sailors see from the lookout of a ship. The ocean continues just as the universe exists beyond the cosmological horizon. We just can't see it. The expansion of the universe is faster than the speed of light, which is why galaxies are far apart beyond 13.8 billion years. Telescopes do not show the world as it is, but as it was. When we look at the stars, we are in fact looking into the past. The farther we look into space, the farther into the past we see. This phenomenon gives us access to bodies or phenomena that no longer exist, such as stars that exploded in supernovae, galaxies destroyed by tidal forces, or the first years of the universe. Light has a speed of 300,000 kilometers per second. It takes time to reach us. It takes about 8 minutes for the light from the sun to reach us on Earth. When we look at the sun, it appears as it was 8 minutes earlier. When we look at the stars in the night sky, they appear to us as they were tens or even hundreds of years earlier. With the expansion of the universe, the concept of distance loses some of its meaning. When a galaxy is 10 billion light-years away, it means that it has been traveling through an expanding space for all that time before reaching us. When this light was emitted, the galaxy was at a closer distance to us than when its light reaches the Earth. Because of the expansion of the universe, astronomers are able to determine the distance to the most distant galaxies in the observable universe. The light that arrives from a galaxy brings with it a suitcase full of information about the length of its journey. The most distant star ever observed is nicknamed Icarus. This blue supergiant is located 9 billion light-years away from us. The galaxy Z8GND 5296 is one of the most distant galaxies and one of the oldest currently known. It would have formed some 700 million years after the Big Bang. Although it is 13.1 billion years old, it is actually about 30 billion light-years away from Earth due to the expansion of the universe. This galaxy appears rich in metals and would generate 100 times more new stars than our Milky Way. Although Laniakea is a most impressive superstructure, it represents only 4% of the observable universe. So what would happen if we took into account the universe as a whole? A long time ago, men thought that our planet Earth was unique. Then we discovered that there were other planets orbiting a star, the Sun. A long time ago, people thought that the Sun was unique. Then we discovered the Milky Way and its hundreds of billions of suns. A long time ago, men thought that the Milky Way was unique. Today we know that the observable universe contains 100 billion galaxies. Is it possible that humans will one day discover that there are other universes beyond the one we are able to observe? To know our place beyond the universe, we would already have to know what it contains. However, this area is currently inaccessible to us. Only hypotheses are put forward by scientists to explain what can be found beyond. The universe that we can observe from the Earth is full of galaxies that extend in all directions. We see them more than 10 billion light-years away. But the galaxies must extend much further. On this subject, speculations abound and address without complex the existence of parallel universes. The string theory of particle physics approaches the notion of multiverse. The different universes of this multiverse would each have unique properties. They could exist in parallel to each other, but in different dimensions. Science also allows us to imagine that beyond the observable universe, space is infinite, and without limit since its creation, it has not stopped growing. The cosmos could then extend perpetually. Hundreds of billions of light-years away from us, there may be another universe similar to ours. In this other parallel universe, would life exist? All research conducted to date in the areas we can reach remains unsuccessful. Beyond the Sun, the Milky Way contains between 200 and 400 billion stars. It is itself only one galaxy among 100 billion other galaxies. Many stars are surrounded by a procession of planets. The list of planetary systems discovered is growing every year. A universe modestly filled with billions of planets could well hide other places where the miracle of life could have taken place. For more than half a century, thanks to highly sensitive detectors and high-tech computers, we have been sending mathematically coded messages to neighboring exoplanetary systems to let them know we are there. But the cosmos remains desperately silent. While it is possible that life is widespread in the universe, complex life forms and intelligent civilizations would certainly be rarer. Perhaps we are a subject of observation for a scientific experiment conducted by an advanced alien life form. Or are we unable to understand them because their technology is much more advanced than ours? Or are we simply the only living beings in the universe? The universe is extremely vast, with billions of galaxies each containing hundreds of billions of stars. Seen from this eye, man occupies a relatively insignificant place. Our planet Earth, being only a small rocky planet orbiting a medium-sized star, the Sun, located in a relatively quiet galactic suburb. Although we have explored and observed much of the observable universe through technology, our understanding remains limited. We know that the universe is expanding and that visible matter, such as stars, galaxies, and planets, is only a small fraction of the total matter in the universe. Man has not yet succeeded in fully understanding the immensity and complexity of the universe that surrounds him. Despite our modest place in the universe, we have developed the ability to think, reason, and understand the physical laws that govern our environment. We have created a technology that allows us to explore and study the universe in which we live. The density of the primordial universe was subject only to slight variations in homogeneity caused by the incessant movement of particles stirred up by radiation. The density perturbations that were created used gravitation. They grew in size, and the force of attraction, caused by their own mass, enabled them to draw matter around them. This is how the gaps in homogeneity that still exist today were created. Theories on galaxy formation are based on two scenarios. The first scenario is based on the hierarchical theory, which implies that the first structures to form were those with a mass sound 1 million times that of the Sun. Larger structures, such as galaxies, formed by agglomerating smaller ones. These galaxies then grouped into clusters, leading to even larger structures, superclusters, which are linked by the force of gravity. Another theory holds that, conversely, the smallest structures are the result of the fragmentation of the largest. In this sense, superclusters would have been created in the first instance. Millions of billions of solar masses would have collapsed under the pressure of gas and radiation. The masses of this entity would then have occupied immense spaces. The expansion of the universe, initiated by the Big Bang, would have forced the great structure and formation to flatten, producing a sheet of dense matter. This sheet then contracted, giving rise to filaments stretching over millions of light years. Over time, these would divide into smaller entities, forming galactic clusters, and then simple galaxies. Over the past few decades, observations of the youngest galaxies have provided further support for both theories. Although there are arguments in favor of both the fragmentation theory and the hierarchical theory, the origin of galaxies is still an open chapter. Galaxies are defined as systems composed of dust, gas, and an astronomical number of stars, all held together by gravity. Most large galaxies also have supermassive black holes at their centers. In 1936, Hubble established a classification of galaxies into 4 types: spiral, elliptical, lenticular, and irregular. Spiral galaxies take the form of a flat disk rotating around a central bulge surrounded by spiral arms. The rotating motion, which can reach speeds of several hundred kilometers per second or miles per second, causes the matter in the disk to take on a particular helical shape. Our galaxy, the Milky Way, is a spiral galaxy. This type of galaxy contains old stars, gas, dust, and young stars. They are generally surrounded by a massive halo of much sparser stars. Elliptical galaxies appear as large, more or less elongated balls of relatively old stars. They therefore appear redder than other galaxies. The space between their stars contains almost no gas, preventing the formation of new generations of stars. Lenticular galaxies are a compromise between spiral and elliptical galaxies. Like spiral galaxies, they consist of a relatively thin disk, rotating around a central bulge, but they have no spiral arms. Like elliptical galaxies, they contain little dust and interstellar matter. Irregular galaxies include original galaxies with very particular shapes that don't fit into any of the other categories. They can resemble twisted disks or distorted balls. Anything seems possible. NGC 4214 is a small irregular galaxy in the Hound Dog constellation, around 13 million light-years away. One of its features, and perhaps the most attractive, is its enormous heart-shaped cavity. Inside it is a gigantic open cluster containing young stars with surface temperatures ranging from 10,000 to 50,000 degrees Celsius, or 18,000 to 90,000 degrees Fahrenheit. This cavity is thought to have formed as a result of stellar winds, and the resulting absence of gas has put a brake on star formation in this area. Galaxies are not isolated in the universe. They move in relation to one another. Sometimes they can pass so close to each other that they cause deformations, shocks, or even absorptions. Even within a galaxy, stars are born and then die, making way for new generations of stars that are very different from the previous ones. The color, brightness, and shape of galaxies are constantly evolving. Galaxies are in perpetual motion. They turn on themselves, move through space, and sometimes collide if they're too close to a neighboring galaxy. When two galaxies cross paths, the more massive one can attract the gas, dust, and stars of the smaller one. As a result, the larger galaxy grows, taking advantage of the smaller galaxy's components to form new generations of stars. The smaller galaxy is then greatly distorted. Sometimes galaxy encounters cause accelerated concentration of gas clouds, leading to outbreaks of star formation. In other cases, a giant galaxy may swallow up a smaller one. The stars and interstellar medium of the smaller galaxy mix with the components of the giant galaxy, resulting in a diverse population of stars. This is known as galactic cannibalism. When galaxies group together in hundreds or even thousands, confined to a spherical space whose evolution is not yet complete, we speak of galactic clusters. These are the largest organized structures in the observable universe. Galactic clusters are structures so large that their construction phase is not yet complete, and they have not yet reached a stable configuration. This means that some objects have not yet reached their point of dynamic equilibrium. Astronomers have thus classified clusters according to their possible evolutionary scenario. There are irregular clusters, generally the youngest, and regular clusters, generally the oldest, with a very high spheroidal galactic central density. In astronomy, different clusters have been identified by their size. These variable dimensions are measured in terms of the cluster's very richness, i.e., its content of bright galaxies over a defined distance of 1.5 megaparsecs from the center. Remember that 1 parsec is equal to 3.26 light-years. The richest clusters are the rarest. Based on this classification, the average distance calculated between two clusters is 42 megaparsecs, whatever the cluster, even for the poorest. On the other hand, to go from one super-rich cluster to another, you need to travel an average distance of 188 megaparsecs. The richness of a cluster determines the type of galaxy it contains. Rich clusters contain a majority of elliptical galaxies. This is because greater richness implies greater galactic density in the inner zones of the cluster. As a result, the richest clusters are generally the most regular. Given that the most regular are also the oldest, galaxies naturally tend to change shape from spiral to elliptical or lenticular. This phenomenon affects the most distant clusters with a large number of blue-colored galaxies, typical of spiral galaxies. The Hubble Space Telescope is making fantastic discoveries in the field of astronomy. Operational since 1990, it features a large mirror, enabling it to deliver images with an angular resolution of less than 0.1 arcsec. Its ability to observe in the near-infrared and ultraviolet enables it to outperform the most powerful ground-based instruments. The data collected by Hubble has contributed to some very important discoveries in the field of astrophysics. Among other things, the telescope has uncovered galactic clusters billions of light-years away. These are spiral and even irregular galaxies that are no longer counted today. There are two possible explanations for their disappearance. Firstly, the merging of two or more galaxies. When a merger occurs, gravitational interactions cause an inevitable morphological change. Computer simulations have shown that the result of a merger is always an elliptical spheroidal galaxy. The other cause of their disappearance is the cessation of new star formation within galaxies. If the gas contained within a galaxy is completely dispersed or consumed, star formation can come to a halt. On the other hand, strong gravitational interactions can cause the gas in a spiral galaxy's disk to escape, leading it to evolve into a lenticular galaxy, or into a galaxy with a disk but no more stars, taking on the colors of an elliptical galaxy. The trend towards galaxy association is not limited to the MPC scale. The local group or group of galaxies forms an immense structure with others in the Virgo cluster. It's a vast flat expanse with a small central bulge, known as the local supercluster. A dozen superclusters are listed on the three-dimensional map of the observable universe. Among the closest are the Hydra centaur, the Hare of Bernice, and Perseus fish. The largest visible structure in the universe is the gigantic Sloan Great Wall cluster. This cosmic structure, forming a giant wall of galaxies, is 1.38 billion light-years long and lies a billion light-years from us. The Great Sloan Wall is about 1/60th the diameter of the observable universe. It contains several superclusters of galaxies. The superstructure of the cosmos that interests us today is none other than the supercluster of galaxies that shelters us. Its name is Laniakea. Laniakea is a supercluster of galaxies comprising a set of 3 superclusters converging at a speed of around 6.30 by 10 to the 5th power miles per second in the direction of the Great Attractor. It is one of 6 million superclusters in the observable universe. It represents around 4% of the diameter of the observable universe, due to its approximate size of 520 million light-years. Laniakea contains 3 superclusters: the Virgo supercluster, to which our planet Earth and the Milky Way belong, the Hydra Centaur supercluster, home to the Great Attractor, and the Peacock Indian supercluster. The Indian Peacock supercluster is located more than 210 million light-years from Earth in the Peacock constellation. It is made up of several thousand galaxies, some of which are very well known and important. The 3 main clusters are Abell 3656, Abell 3698, the densest, and Abell 3742. It incorporates a nearby galaxy wall, linking the Ruler cluster to the Centaur supercluster. A galaxy wall defines a galactic filament made up of a set of galaxies forming a boundary between cosmic voids, which together make up the cosmic web. The Indian Peacock supercluster contains no rich galactic clusters, nor any particularly large concentrations of galaxies. It is therefore not considered a major component of Laniakea. In the sky, it is faintly discernible as a curved wall of galaxies, linking the A3627 or Ruler cluster and the Centaur supercluster. The Hydra Centaurus supercluster is one of the largest known galaxy superclusters, covering an area of several tens of millions of light-years. It contains many important celestial objects. It is the nearest neighbor of our own Virgo supercluster. The supercluster is divided into several parts. The Centaur supercluster, which includes the Centaur cluster, the Hydra supercluster, which mainly contains the Hydra cluster, and the Ruler cluster. These clusters lie between 150 and 200 million light-years apart. Other, smaller clusters complete the picture. One of the features of the Hydra Centaur supercluster is its proximity to the Great Attractor. The latter is a gravitational anomaly in intergalactic space at the center of the Laniakea supercluster. The Virgo supercluster, also known as the local supercluster, is a supercluster of galaxies to which the local group, comprising the Milky Way and Andromeda galaxies, belongs. It owes its name to the Virgo cluster at its center. Its diameter is around 200 million light-years. The Virgo supercluster consists of a disk and a halo. The disk is circular in shape and contains 60% of the supercluster's luminous galaxies. The halo, on the other hand, is made up mainly of elongated objects and contains the remaining 40%. Within the Virgo supercluster, there are some 10,000 galaxies and over 100 clusters. The Virgo cluster is located close to its center, while the local group is close to the edge, but attracted by it. Its total mass is estimated at around 10 to the 15th power solar masses. As its luminosity is relatively low compared with the number of stars it contains, scientists agree that a large proportion of it must be made up of dark matter. All the objects in the Virgo supercluster are gravitationally attracted to the Great Attractor. The Virgo supercluster is unbundled into clusters called clouds of galaxies. The disk contains the Virgo cluster, the Hound cloud, and the Virgo II cloud. In 1964, two Americans accidentally discovered a form of radiation in which the entire universe is immersed, the cosmic microwave background. It was then that they discovered that our galaxy was moving at an astronomical speed of 630 kilometers per second, or 390 miles per second. At the time, the phenomenon was not fully explained, and teams of astronomers were formed to investigate it further. The Seven Samurai, a team of 7 American astronomers, supported and studied this shift. After 20 years of research, they succeeded in measuring the speed of displacement on a sample of around 400 galaxies. They also succeeded in delineating the zone that seems to be attracting our galaxy. However, the latter is occulted by our own galaxy. The stars forming a luminous band on the celestial vault mask precisely the location that interests the scientists. Scientists agree that our galaxy is not alone in moving at 630 kilometers per second or 390 miles per second, but that all the galaxies around us are moving in the same direction through the cosmos. The Seven Samurai couldn't explain this phenomenon with the physics of the time, so they came up with a model. It would be a gigantic obscure mass, invisible to us but attracting us. This enormous mass is known as the Great Attractor. Although telescopes at the time were not powerful enough to observe it, resources were deployed to improve observation tools and succeed in discovering this curious Great Attractor. In 2014, researchers discovered that we belong to an even larger structure. While trying to map the direction in which thousands of galaxies are moving, researchers discovered that the local group is part of the Laniakea supercluster. The local supercluster is, after all, only a lobe of a supercluster comprising 100,000 large galaxies and extending over a distance 10 times greater. Scientists discover that the Great Attractor is not simply a huge spherical obscure object, but the central point of a celestial continent towards which objects are gravitationally directed. All this represents only 4% of the mapped universe. The newly discovered gigantic supercluster is named Laniakea in honor of the early Polynesians who explored the Pacific Ocean using the stars as a guide. Laniakea means immense celestial horizon in the Hawaiian language. It measures over 520 million light-years in diameter. It is surrounded by other superclusters such as Shapley, Hercules, and Perseus Pisces. Within Laniakea itself, different forces influence the movement of galaxies. Thanks to the discovery of Laniakea, we are learning more about the architecture, dynamics, past and future of the universe. The distribution of galaxies and their movements give us valuable information about the history of their formation. Within the borders of Laniakea are a multitude of small and large galaxies with a mass equivalent to 100 million billion times the mass of the Sun. The supercluster of galaxies in which we live is immense and could be defined as follows. Take our galaxy, multiply it by 100,000, add 1 million smaller galaxies, and you get Laniakea. We begin our journey in the direction of the one that lies at the center of Laniakea and has the greatest influence on its members. This is the Great Attractor. As early as the 1970s, the first signs of a deviation from what is supposed to be a uniform expansion of the universe were detected. In 1986, the position of the so-called Great Attractor was defined. This is a gravitational anomaly at the center of Laniakea, in the vicinity of the Hydra-Centaur supercluster. It is difficult to observe because it lies directly behind the galactic plane of the Milky Way. The Great Attractor can be detected indirectly through its effect on the motion of galaxies and clusters. The expansion of the universe explains why galaxies are constantly moving further apart. However, huge clumps of matter can slow down this movement. Over the past billions of years, our galaxy, and all the galaxies around us, have moved closer to the Great Attractor. There are several theories about the nature of the Great Attractor. It could, for example, be caused by an overdensity of matter. The Great Attractor remains a mystery. It lies on the other side of the Milky Way, with an enormous number of stars and star clusters positioned between them and us. Added to this is a jumble of gas and dust. The light that is supposed to reach us is consequently obscured, making it difficult for scientists to observe. The only certainties are that our galaxy, and everything in our supercluster, is heading towards the Great Attractor. Does this put our planet at risk? No one really knows at present. While some astronomers don't see it as a problem, others think that galaxies and all the clusters could coalesce into ever larger superclusters, eventually causing the end of the universe in the form of a big crunch. Let's continue our journey in our closest neighborhood, astronomically speaking, since we're talking about visiting distances of the order of thousands of light years. The Milky Way, our own galaxy, is the one we know most about in detail. Studying it enables us to better understand the world around us and the parts of the universe to which we have no access. We live on Earth. Our planet lies close to the Sun, which in turn lies on one of the arms of our spiral galaxy called the Milky Way. The Earth is launched into its orbit at around 30 kilometers per second or 19 miles per second around the Sun. The Sun drags the entire solar system along at a speed close to 220 kilometers per second or 136 miles per second. Although these speeds seem dizzying, the Milky Way is so vast that we're only about half the length of the arm. If we were to compare the Earth to a marble, 1 millimeter in diameter, the Moon would be 3 centimeters or 1 inch away. The Sun would be 1.5 meters or 5 feet away, and the nearest star, 3,200 kilometers or 2,000 miles. The Milky Way would then have a diameter extending to half the distance separating us from the Sun. The Earth is infinitely tiny in this system that surrounds it. Over the past few centuries, mankind has become increasingly aware of the immensity of the stellar world, and has been scrutinizing it ever more closely, mostly from a distance. Seen from Earth, the spectacle of the Milky Way is awe-inspiring, even without any instruments, especially when you're in the southern hemisphere, as the luminous regions of the galactic center shine high in the sky. The Milky Way remains one of the most important targets in the exploration of the universe. Although the distances are gigantic, it provides us with an accessible laboratory of the universe, where a panoply of objects representative of the stars and other celestial objects that populate our galaxy can be found up close. Within the Milky Way, elementary physical processes are also taking place that can be analyzed. Scientists agree that the Milky Way is a representative prototype of the spiral galaxies that make up the largest class of galaxies today. Exploring the Milky Way, therefore, provides us with elements to explain this type of galaxy throughout the universe. What's more, man's origins are rooted in the Milky Way. It is like our cosmic habitat in which our solar system was formed. The Milky Way is a spiral galaxy with a diameter of 100,000 light-years and a thickness of just over 1,000 light-years. It was formed billions of years ago, when an immense cloud of gas collapsed under its own gravity and flattened under the effect of rotation. It consists of a central bulge, around which two main spiral arms and segments of other arms are articulated. Their shape is shaped by bright young stars, gas and dust nebulae, and dense dark molecular clouds. The central bulge contains many old stars but little gas. The Milky Way is roughly the shape of a very thin disk. It contains between 200 and 400 billion stars. Although this figure seems extraordinary, the total mass of stars occupies only a tiny total volume on the scale of that of the galaxy. Stars are scattered all over the galaxy's great void, but this vacuum of space is occupied by extremely tenuous interstellar gas. Galaxies are made up of stars, dark matter, various exotic components, and interstellar gas, which is diluted in this gigantic volume between each star. Interstellar gas is extremely dilute, containing an average of 1 atom per cubic centimeter. Compared to the air we breathe, this is more than 10 billion times less. It is from this interstellar gas that new stars are formed. Proto-galaxies were initially nothing but gas. Then, over billions of years, galaxies like the Milky Way expanded by accreting gas from outside the galaxy. It was interstellar gas that gave spiral galaxies their disk shape. A ball of gas can be compressed along its axis of rotation by its own gravity. A disk forms perpendicular to this axis. Interstellar gas can be cold atomic, hot atomic, molecular, hot ionized, or very hot ionized. Cold atomic gas accounts for about half of its total mass. It is an indispensable reservoir that feeds the molecular clouds in which new stars are formed. Molecular gas is the natural state of most gases, neither too hot nor too dilute. Interstellar molecular gas accounts for roughly 1/3 of the total mass of gas in the Milky Way. It is not homogeneous and is scattered with lumps. These small, dense clouds are ideal sites for the formation of new stars. The density and temperature conditions of interstellar gas lead to the presence of some quite extraordinary molecules. These highly reactive species, which are fleeting in our laboratories, play a key role in the chemistry of the interstellar medium. They are created by reactions initiated by cosmic rays or ultraviolet radiation. A galaxy like the Milky Way is largely composed of a gas in which all hydrogen atoms are ionized. Each star is surrounded by a bubble of denser gas, ionized directly by ultraviolet photons. The distribution of stars in interstellar gas is totally dominated by the disk structure, but the importance of peripheral regions should not be underestimated. Gas in stars can extend far into the exterior of the disk. A spherical region, called the galactic halo, contains one of the oldest stellar populations in the galaxy, as well as mysterious dark matter. The central region of the galaxy stands out for its originality. The bar shapes the structure of the central disk, enabling it to be fed with gas, and thus support dynamic star-forming activity. The bulge of the galactic bulge bears witness to earlier star formation in these regions. A large black hole of several million solar masses remains at its center. This supermassive black hole at the center of the Milky Way remains modest in comparison with the black holes at the center of giant elliptical galaxies. Despite its mass of 4.2 million solar masses, it remained unknown until 1974. This Milky Way black hole remains dormant due to the lack of accretion of large quantities of gas, so its environment emits only modest energy. Since its discovery, scientists have been wondering whether this black hole is likely to wake up in the not-too-distant future and become an active galactic nucleus. The stability of the Milky Way would seem to give us peace of mind for the next few 100 million years. However, gas accretions can occur regularly, gradually increasing the power of this radio source. The galactic center is therefore closely monitored. The interstellar medium is made up of dust composed mainly of silicate or graphitic carbon. They range in size from a few micrometers to a few nanometers. They absorb UV radiation, protecting the molecules inside molecular clouds. The dust is constantly exchanging molecules and atoms with interstellar gas. Supernova explosions have a significant impact on the state of the interstellar medium. The energy released at immensely high velocity greatly upsets the surrounding interstellar medium. It becomes highly ionized, full of energy, and emits a peculiar radiation at all wavelengths. This is why remnants of historic supernovas, such as the Crab Nebula, stand out against the galactic sky. As the most massive stars have relatively short lifetimes, their supernova explosions frequently occur in the environment of the giant molecular cloud in which they formed. Cosmic rays are the most energetic component, directly linked to the violence imputed to the interstellar medium by supernovas. Their energy is sufficient to penetrate to the heart of molecular clouds, where they are a source of gas, heating, and the origin of all interstellar chemistry. The interstellar medium is marked by the universal action of the magnetic field on moving charges. The interstellar magnetic field is on average 30,000 times weaker in the Milky Way disk than the Earth's magnetic field. Interstellar magnetic fields are generated by currents of electric charge created by a kind of natural dynamo. Even if this force is not very intense, it is able to bend the trajectories of charged particles in a spiral around the magnetic field, since it is applied over astronomical timescales. Astronomers have traced the spiral structure of our galaxy, even though it is impossible to see it from the outside. Infrared images provided by the Spitzer telescope have revealed that the Milky Way is dominated by just 2 arms. The galaxy was once thought to be made up of 4 main arms, but 2 of these have now been downgraded to secondary arms. The 2 main arms are the Centaur arm and the Perseus arm. They surround a central core of young and old stars. The secondary arms are the Ruler or Cygnus arm and the Sagittarius arm. They are mainly composed of gas and contain numerous stellar formations. Between Sagittarius and Perseus lies a small partial arm called the Orion arm, in which our Sun is located. The Perseus arm takes its name from its apparent proximity to the constellation Perseus. It lies between the Ruler arm and the Sagittarius arm. Some interesting celestial objects can be found here. The explosion of a supernova is as impressive as the appearance of a comet. Centuries ago, astronomers and astrologers recorded these strange celestial events. In July 1054, Chinese chronicles reported the appearance of a bright new star in the Taurus constellation. This star remained visible for several days, even during the day. In 1731, an English astronomer discovered a small faint nebula in the Taurus constellation. It was later nicknamed the Crab Nebula because of its shape. It lies around 6,500 light-years from Earth and has a diameter of around 10 light-years. In the early 20th century, astronomers discovered that the Crab Nebula was expanding. Thanks to backward calculations, it became clear that the moment when its expansion began coincided with the appearance of the star of 1054. The Crab Nebula represents the expanding shell of gas created by the supernova explosion seen in 1054. It continues to grow at a speed of 1,500 kilometers per second, or 930 miles per second, and will continue to dilute in space over the coming millennia. At the center of the nebula is a pulsar that rotates on itself around 30 times per second. It radiates 200,000 times more energy than the Sun. The Crab pulsar is at the origin of the nebula and responsible for its central radiation. Pulsars emit strong electromagnetic radiation, briefly and regularly, several times a second. They are formed by supernova explosions. They are fast-rotating neutron stars whose magnetic fields concentrate the radiation they emit into a fine beam. The Crab pulsar measures around 28 kilometers or 17 miles in diameter. It emits pulses every 33 milliseconds, but this frequency gradually decreases, indicating that the pulsar is slowing down. The region around the pulsar is particularly dynamic due to the energy emitted. The progenitor star is the one that exploded into a supernova and formed the nebula. It was a massive star. When the core of a massive star collapses in on itself, it congeals into an iron core. The atmosphere collapses and bounces off this core, triggering an explosion. It leaves behind an object, in the case of the Crab Nebula, a pulsar. The progenitor star had a mass of around 10 solar masses. The filamentary structures of the nebula are not visible to the naked eye and can only be observed through a telescope. The Centaur arm lies between the Sagittarius arm and the ruler arm. It is also known as the Echo-Croy arm. The section of the arm begins near the galactic center and forms the Echo arm. It becomes the cross arm as it moves away from the center. In 2007, a cluster containing around 50,000 newly formed stars was discovered in an area of the Centaur arm. The cluster is less than 20 million years old. Within it, 26 supergiants have been identified, making it the largest grouping of such stars. The ruler arm is named after its proximity to the ruler constellation on the celestial sphere. Its source is at the end of the central bar, not in the surrounding region. The ruler arm is defined by the part of the arm that is close to the galactic center. The outermost parts of the arm are called the swan arm. For this reason, it is often referred to as the ruler swan arm. The Sagittarius arm is one of the two longest in the galaxy, along with the ruler arm. Its end, closest to the bar, is connected to the end of the bar itself. The Sagittarius arm is rather dense. It lies between the Centaur arm and the Orion arm, close to the constellation Sagittarius. The part of the arm that emerges from the central bar is called the Sagittarius arm, while the outermost part is called the Carina arm. Several stellar objects are visible in the Sagittarius arm. The Lagoon Nebula, also known as M8, is located around 4,000 light-years away, at a point in the Sagittarius constellation where this type of object is found in large numbers. That is, in fact, the richest region of the Milky Way, as it faces the center of the galaxy. Dust clouds are almost always found on the galactic plane. The Lagoon Nebula is associated with an open cluster. Nebulae, which are star-forming zones, are often accompanied by clusters of young, brightly scintillating stars. Within this open cluster are some 40 stars with magnitudes between 8 and 13. This brightness excites the nebula's atoms, making it visible. Also visible within M8 are various Bok globules, dark clouds of dense gas and dust where stars form. The Trifid Nebula, also known as M20, owes its name to its characteristic three-part shape. It is thought to be around 4,000 light-years away. With binoculars, the bright part of the nebula can be seen perfectly, in the shape of a round spot. The darker parts that divide the nebula into flaps are caused by the presence of dust and cold gas. M16, the Eagle Nebula, lies at the edge of the Shield constellation, close to the Serpent constellation. Its distance is estimated at around 5,000 light-years. Within the nebula itself is a dark region that stretches from the north towards the center of the nebula. The associated cluster consists of several dozen stars, some of which are faintly visible and red. Although this is a nebula in emission, it has some reflective features. M11, the Wild Duck Cluster, is the richest open cluster in the sky. It comprises almost 3,000 members and is located just over 6,000 light-years away. The cluster is so crowded that the distance between stars towards the center of the object is tens of times smaller than the average distance in the Milky Way. Its stars are relatively young, between 200 and 250 million years old. Viewed from Earth through a telescope, the stars appear to be arranged in a V-shape, so much so that this magnificent cluster has been likened to a flight of wild ducks, hence its name. The Omega Nebula, also known as M17, is one of the most contrasting diffuse objects in the sky. With the aid of binoculars, you can identify its central spindle-shaped region, which gleams not far from a beautiful orange star. The luminous curves of this nebula suggest that it is made up of exceptional quantities of gas. And yet, the mass of this nebula is equivalent to less than 1,000 suns. Nonetheless, it remains one of the most imposing nebulae in the Milky Way, extending over almost 50 light-years. The Omega Nebula is the birthplace of one of the youngest star clusters known, less than 1 million years old. The cluster contains some 35 stars at most, but the total number of stars in the nebula is around 1,000. It's one of the most fertile star nurseries in the Milky Way. The Orion Arm is a minor arm of the Milky Way. It is in this arm that the solar system, and therefore the Earth, is located, close to the lower edge some 26,000 light-years from the galactic center. The Orion Arm lies close to the constellation Orion, between the Sagittarius Arm and the Perseus Arm. It is estimated to be 10,000 light-years long and 3,500 light-years wide. The Orion Arm contains several recognized objects. The Orion Nebula, named M42, is the closest to Earth at 1,300 light-years. This diffuse nebula is home to numerous star-forming stars and even planetary disks. The Orion Nebula is visible through binoculars as a small cloud amid the stars of Orion's sword. It glows fluorescently. Ultraviolet radiation from bright stars excites gas atoms, which in turn emit light. The color emitted differs according to the type of atom. Hydrogen and sulfur emit mainly red light. Oxygen glows green. Although our eyes can't distinguish colors very well at night, and all nebulae generally appear gray to the telescope, the Orion Nebula is an exception to the rule. The Orion Nebula is an exception to the rule and makes it easy to observe the different colors of a nebula. Also known as M45, the Pleiades cluster has been known since Neolithic times. Its appearance in the morning sky heralded the harvest season. It is located 440 light-years from Earth, and although only a small number of stars are visible to the naked eye, this open cluster contains several thousand. The Pleiades cluster is 100 million years old. In 200 to 300 million years' time, it is likely to be completely dispersed in the Milky Way due to its low density. The origin of the name Pleiades comes from Greek mythology. Children of Atlas and Pleione, the Pleiades are 7 sisters. Their names and those of their parents were given to the 9 brightest stars in the cluster. The best-known planetary nebula is the Lyra Nebula, known as M57. It is located in the constellation Lyra and is difficult to identify due to its low surface brightness. It lies around 2,300 light-years from Earth and is between 3,000 and 6,000 years old. The name Planetary Nebula comes from the fact that early observers mistook these objects for planets due to their circular shape. In reality, they are formed by the emission of a gas envelope from stars at an advanced age in their evolution. Its characteristic shape has also earned it the nickname Ring Nebula. The inner region of the ring emits ultraviolet rays, making it appear darker. The central regions emit blue-green hues from doubly ionized oxygen. The outer regions of the ring appear red. The central star is a white dwarf, slightly larger than the Sun, with an apparent magnitude of 14.8. The Dumbbell Nebula, or M27, is located in the constellation of the Little Fox. Thanks to simple, small amateur telescopes, it's possible to make out its bell-shaped form. It has 2 luminous lobes. It's a bipolar-type structure that exists in other planetary nebulae, but rarely so pronounced. Planetary nebulae dilute in space at speeds of several tens of kilometers per second. As a result, they don't remain visible for more than a few thousand years. There are very few of these nebulae to be seen in the sky. The Dumbbell Nebula remains one of the largest in the sky because it is close to us, less than 1,400 light-years away, and its age means that it is widely spread out. The Owl Nebula is a planetary nebula around 2,380 light-years away. It is also known as M97. Around 6,000 years old, it is located in the Big Dipper constellation. Its name derives from its cylindrical torus shape, which appears oblique when seen from Earth. The 2 holes at the ends, which are less rich in matter, resemble the eyes of an owl. Although our own galaxy is still the one we know best, astronomy is making our neighborhood seem less alien. The Andromeda Galaxy, also known as the Great Andromeda Nebula until its true nature was recognized in the 1920s, is the largest spiral galaxy in the vicinity of the Milky Way, and the largest member of the local group. It is located around 2.5 million light-years from the Sun, in the direction of the northern constellation Andromeda. With a diameter of 120,000 light-years, it is twice as massive as the Milky Way. However, its dynamics and composition are similar. At its center is a compact stellar cluster with a double structure. The Andromeda Galaxy is one of the few galaxies that can be observed with the naked eye in the northern hemisphere from Earth. It is one of the largest objects in the sky, containing around 1,000 billion stars. It is thought to have formed less than 3 billion years ago, when the Earth already existed, as a result of the collision of 2 other galaxies. A first galaxy, already present, was struck by a second, 4 times smaller than the first, 4 billion years ago. This collision caused the 2 galaxies to merge, giving rise to the Andromeda Galaxy between 1.8 and 3 billion years ago. Like our own Milky Way, the Andromeda Galaxy is a giant spiral galaxy, surrounded by smaller companions. There are some 460 globular clusters associated with the Andromeda Galaxy. Myal 2, also known as G1, is the most massive and brightest of the local group. It contains several million stars of different generations. Around 20 dwarf galaxies orbit the Andromeda Galaxy. The most massive is the Triangulum Galaxy. M32, an elliptical dwarf galaxy still visible at the edge of the Andromeda Galaxy's disk, despite its great discretion. It seems to be the source of morphological disturbances within the Andromeda Galaxy. M33, or the Triangulum Galaxy, is the third largest object in the local group. It is modest in comparison to the Milky Way and Andromeda galaxies, containing just 40 billion stars. Its spiral arms are well developed and appear spectacular when seen from the front. Its immense tentacles of cold gas extend far beyond the visible disk, making it difficult to give a precise value for the Triangulum Galaxy's diameter. Its distance from Earth is also uncertain, estimated at between 2.5 and 3 million light-years. In the end, it would appear to be only slightly further away from us than the Andromeda Galaxy, even if it looks much more distant to the naked eye. Along its arms are numerous regions of ionized gas, a prime site for star formation. The largest of these nebulae, the Triangulum Nebula, bears the number NGC 604. It is 6,000 times brighter than the Orion Nebula and extends over 1,500 light-years. It is an emission nebula. Its gas is ionized by a cluster of massive stars inside its core. Within the Triangulum Nebula itself, some 200 stars are distributed in at least 2 clusters. The Great Dog Dwarf Galaxy is the closest known galaxy of any class to the Milky Way, since the nearest spiral galaxy is the Andromeda Galaxy. It lies 42,000 light-years from the galactic center and around 25,000 light-years from our solar system. It is home to 1 billion stars, equivalent to 1% of the Milky Way. The tidal forces of the Milky Way are currently tearing the Big Dog Galaxy apart. The center is relatively degraded, with a long filament of stars trailing behind in a ring. Located near the Eridon group, the Furnace cluster boasts around 58 galaxies. The brightest in the cluster is NGC 1427a, an irregular galaxy. It crosses the cluster at a relative speed of around 600 kilometers per second, or 370 miles per second. The Furnace cluster contains 4 times fewer galaxies than the Virgo cluster, but is around twice as dense. NGC 1427a's interaction with its surroundings favors star formation and gives the cluster its distinctive arcuate shape. The Eridon cluster is a cluster of galaxies whose center lies around 75 million light-years from Earth. It is located in the Eridon constellation. It contains around 200 galaxies, with approximately 30% elliptical or lenticular galaxies and 70% spiral or irregular galaxies. This barred spiral galaxy is located around 69 million light-years from Earth. It is known for its luminous center and well-developed spiral arm structure. Indeed, most star bars remain imperceptible, as is the case with our own Milky Way. But NGC 1300's star bar is spectacular. This bar also plays a significant role in the evolution of the galaxy, as it increases star formation within it. The core of NGC 1300 itself has a small spiral winding extending over some 3,300 light-years. This phenomenon is due to the fact that this spiral galaxy has an imposing central bar. Located around 65 million light-years from Earth, this spiral galaxy is remarkable for its clearly visible disk with spiral arms and central bar. It is known as a grand spiral galaxy. Its spiral arms extend clearly around the galaxy and can be seen at a good distance around the nucleus. NGC 1232 is located in the Eridan constellation. This is one of the most massive galaxy clusters in the Hydra-Centaur supercluster, around 220 million light-years from Earth. It contains several bright galaxies, as well as clusters of hot gas and dark matter. Its mass is around 10 to the 15th power solar masses. It is also known as the Ruler Cluster. It lies close to the Great Attractor. Although it is relatively close to us and visible, it is nevertheless located in what is known as the avoidance zone, an area close to the galactic plane of the Milky Way that is consequently difficult to observe. The cluster is thus obscured by interstellar dust. Able 3627 is located in the Ruler constellation. This constellation, which has seen its borders modified, is not home to alpha or beta stars, which are found in neighboring asterisms. The brightest star in this constellation is Gamma 2, magnitude 4. The Ruler cluster contains two interesting nebulae, NGC 6164, 6165, and Shapley 1. NGC 6164-6165 refers to two lobes of the nebula in emission. The nebula's gas has been ejected by the star at its center. This star is the source of the nebula's energy. The star is relatively young, between 3 and 4 million years old. It is around 40 times more massive than the Sun. Shapley 1 is a planetary nebula that describes an almost perfect circle. It is located some 4,900 light-years from Earth. Its magnitude is 12.6. The white dwarf at its center has a magnitude of 14. NGC 4696 is a giant elliptical galaxy in the Centaurus galaxy cluster, part of the Hydra-Centaurus supercluster. It is known for its active nucleus, which produces high-energy jets of matter. It is the largest galaxy in the Centaurus cluster. It is surrounded by several elliptical dwarf galaxies. Dust filaments surround the center of the immense galaxy. These wind inwards like a spiral, swirling around a possible supermassive black hole. This barred spiral galaxy is located in the constellation Centauri, some 13 million light-years from Earth. It is known as one of the brightest galaxies in the region. Two supernovas have been discovered in NGC 4945. The supernova SN 2005AF Type 2 and SN 2011JA Type IIP. NGC 4945 is thought to belong to the Centaurus A group. This group, of at least 8 galaxies, is located in the constellation Centaurus. This is an active Seyfert-type lenticular galaxy in the Centaurus constellation, more than 200 million light-years from Earth. It is known for its active core, which produces high-energy X-rays and radio waves. Until the middle of the 20th century, scientists believed that galaxies were relatively quiet objects. In 1943, astronomer Carl Keenan Seifert discovered the existence of astonishing phenomena inside the nuclei of certain galaxies, such as abnormally high radio wave emission, blue light emission from central areas, and luminosity variations. It has since been demonstrated that the nuclei of different types of galaxies are in fact active. Names have since been assigned to distinguish them. These include radio galaxies, Markarian galaxies, Seifert galaxies, quasars, and BL, Lacertae objects. Today it's accepted that these are all manifestations of objects belonging to a single family, active galactic nuclei, or AGNs. The driving force behind these active galactic nuclei is a black hole with a mass of between 100 million and 1 billion solar masses. IC 4329 is the brightest galaxy in the IC 4329 galaxy group. This group has at least 25 members. It contains a large number of vast galaxies. Located around 28 million light-years from Earth, this galaxy is famous for its flattened disk shape with an obvious central bulge, resembling a Mexican hat. Although smaller than our own Milky Way, this galaxy, known as M104, is extremely massive. It is thought to contain 1,000 billion stars and over 1,000 globular clusters. From Earth, we can observe this galaxy almost in profile, as its axis of rotation is tilted 84 degrees to our line of sight. This gives us a view of the immense dust disk that divides it in two. This object is one of the most photogenic in the universe. Its diameter reaches 50,000 light-years, and its mass is equivalent to 800 billion solar masses. The diffuse light emitted by the central swelling is due to billions of ancient stars and globular clusters. The Sculptor group is the galaxy cluster closest to the local group. This group of galaxies is located near the edge of the Indian Peacock supercluster and contains several important galaxies, such as the Spiral Galaxy, NGC 253. These celestial objects are important for our understanding of the structure and evolution of the Indian Peacock supercluster, and of the universe as a whole. The Sculptor Galaxy, also known as NGC 253, is an intermediate spiral galaxy around 10 million light-years away in the Sculptor constellation. This galaxy has a high rate of incipient star formation. It is the most massive member of the Sculptor group. Its core is believed to house a supermassive black hole with a mass equivalent to around 5 million solar masses. This galaxy is visible through binoculars when the sky is free of light pollution, as it is one of the brightest galaxies in the sky after the Andromeda Galaxy. The dwarf Sculptor Galaxy and the irregular galaxy NGC 55, although both present in the constellation Sculptor, belong to the local group. NGC 1316, also known as Fornax A, is a giant elliptical galaxy around 61 million light-years from Earth. It is famous for its galactic fusion activity and intense source of X-ray radiation. The Laniakea supercluster is home to billions of stars. Among them is Sirius. Characterized by its magnitude, 1.5, Sirius is the brightest star in the sky. It shines 25 times brighter than the Sun, yet some stars shine thousands of times brighter. In fact, it's Sirius's proximity to the Sun that makes it appear so bright. It is the fifth closest star to Earth. In ancient times, Sirius was of particular importance, since its return to the sky at dawn heralded the flooding of the Nile, crucial for agriculture. Canopus is a supergiant star 71 times larger than the Sun. It lies around 310 light-years away. It is the brightest star in the constellation Carina, and the second brightest in the night sky after Sirius. Its magnitude is 0.74. Not massive enough to eventually evolve into a supernova, it is likely to become a white dwarf. "200 billion stars populate the Milky Way, but only those not far from the solar system can be seen with the naked eye. The closest is Alpha Centauri. It's a complex star made up of 3 stars. The 2 largest form a beautiful double star, 4.37 light-years from the solar system. Their size and color are similar to those of the Sun. They are accompanied by Proxima Centauri, a faint, tiny star, barely 1.5 times the size of Jupiter. It lies closer to us than the other 2, at 4.22 light-years. Proxima Centauri holds the record for proximity to the Sun. Located in the Lyra constellation, Vega is the brightest star in this group. Observed from Earth, it is the 5th brightest star in the sky. It is relatively close to the Sun, just over 25 light-years away. Because of its high luminosity, Vega has been the subject of numerous studies by astronomers and has played a major role in astronomical discoveries. For example, it was the first star outside the Sun to be photographed and its spectrum measured. It has a disk of dust centered on the star, probably the result of collisions between objects in a debris disk, similar to the solar system's Kuiper belt. In the Orion constellation, a variable red supergiant star known as Betelgeuse shines brightly. It lies approximately 500 light-years away. It is one of the largest stars known. If positioned at the center of the solar system, its radius would stretch between the orbits of Mars and Jupiter. It used to be considered the 8th brightest star in the sky, but in 2019, a drop in its brightness pushed it down to 21st place. One explanation for this phenomenon was the formation of dust in front of the star, following the ejection of a large quantity of gas. In subsequent years, the star's luminosity increased again, reaching almost 87% of its original brightness. Betelgeuse radiates more than 100,000 suns combined. Eventually, it will explode into a supernova, which can easily be observed from Earth in broad daylight. To us, Laniakea is an immense cosmic structure in the observable universe, encompassing our own Milky Way galaxy, as well as thousands of other galaxies. Spanning some 520 million light-years in diameter, it is one of the largest known structures in the universe. Yet Laniakea is only a small part of the observable universe, which contains billions of similar superclusters, as well as regions of intergalactic void. The discovery of Laniakea has enabled scientists to better understand the large-scale structure of the universe and its evolution, as well as our galaxy's place in this vast expanse of space. Yet this journey remains incomplete, with many secrets and mysteries yet to be discovered. A century ago, the 100,000 light-year diameter of the Milky Way represented the cosmic horizon, and from our vantage point on Earth, we already felt infinitely small. Since then, discoveries have continued to push back this limit. This exploration of the cosmos amplifies our vertigo in the face of the abyss into which we are plunged